Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are stepping softly into one of the strangest little mysteries in all of physics, a mystery so odd that if it happened on the scale of everyday life, you would probably spill your tea, check your door locks, and begin to wonder whether the universe had forgotten some of its own rules. We're going to talk about quantum tunneling, the peculiar way tiny particles can sometimes pass through barriers that, by ordinary logic, they really ought not to pass through at all. Not climb over them, not break them, not drill through them with a microscopic spoon. Just appear on the other side, as if reality itself has a few hidden drafts beneath the doors. Now, if that sounds impossible, that is a perfectly reasonable reaction. In the world we know, walls are very committed to being walls. A closed door does not let you through simply because you feel optimistic. A tennis ball thrown at a brick wall does not politely consider the possibility of being found on the far side. It bounces back, usually with a disappointing thud, and perhaps with a small lesson about aim. A person cannot lean gently against a mountain and, after a moment of quiet concentration, emerge on the other side with a sandwich and a new appreciation for geology. The ordinary world is full of barriers, and those barriers take their jobs seriously. They hold things in, keep things out, divide rooms, support roofs, protect biscuits, and generally prevent reality from becoming too confusing before breakfast. But the quantum world, as it so often does, raises a tiny hand from the back of the classroom and says, actually, it is not quite that simple. Down at the scale of atoms and particles, things do not behave like miniature versions of the objects on your desk. An electron is not just a little bead rushing around like a speck of dust. A proton is not simply a billiard ball wearing a very small waistcoat. These things belong to a realm where position is not always definite, where motion is not always a neat path, and where the possible has a strange habit of leaking into places where the impossible seem to be standing guard. Quantum tunneling is one of the clearest signs that nature, at its smallest scales, does not always follow the comforting rules our brains evolved to expect. Before we drift too far into that strange and gentle landscape, let me ask you something. Where in the world are you listening from tonight? Are you tucked away in a quiet room, perhaps with the light low and the day finally loosening its grip? Are you listening in the early hours, when the streets outside seem to belong to cats, delivery vans, and people making questionable decisions with toast? Or is it morning where you are, and this little journey into the quantum world is keeping you company with a cup of something warm? And since tonight we're speaking of particles passing through barriers, what sort of wall is nearest to you right now? A bedroom wall, a window, a door, perhaps the invisible wall between being awake and almost asleep. Fitting, really, because as you listen, your thoughts may begin to do their own kind of tunneling, slipping gently past the solid worries of the day and arriving somewhere quieter on the other side. If you find this journey soothing, intriguing, or simply a comfortable way to let your mind wander after a long day, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this quiet corner of science reach other curious minds who might also enjoy learning something peculiar while slowly becoming less determined to stay awake. And if you already have subscribed, then thank you, truly. You're helping keep the kettle warm, the chalkboard dusted, and the tiny imaginary particles politely ignoring barriers in an educational fashion. Now, I do hope this topic does not become so fascinating that it keeps you wide awake, staring at your bedroom wall and wondering whether any of your atoms are planning a midnight escape. But if it does, at least you will have something wonderfully strange to think about while the rest of the house settles down. So settle in, let your shoulders drop a little, let the day stretch out behind you. We will move slowly because quantum tunneling is not something that needs to be rushed. In fact, rushing at it with too much confidence is a fine way to bounce straight off the subject, much like a ball hitting a garden fence. Instead, we will approach it gently, from the familiar world of walls and locked doors into the mistier world of probability, atoms, stars, and the hidden workings of modern technology. Somewhere along the way, we will discover that this odd phenomenon is not just a strange trick in a physics textbook. It helps explain how the sun shines, how certain forms of radioactivity happen, how special microscopes can feel the surface of atoms, and why the electronics around us depend on the quiet, slippery habits of particles that refuse to behave like sensible little marbles. To begin, imagine a hallway with a door at the end of it. The door is closed. You walk up to it, place your hand on the handle, and try to go through. If the door is unlocked, no problem. If it is locked, then the story becomes much more classical. You either need a key, a locksmith permission, or, if this is a very dramatic film, a shoulder and a complete disregard for the deposit on the building. The point is simple. In everyday life, crossing a barrier requires enough energy, enough force, or the right route. If you do not have those things, you do not pass. That rule is so deeply woven into ordinary experience that it barely feels like a rule at all. It feels like common sense. A child learns it very early. Blocks cannot pass through blocks. A toy car cannot drive through the side of a wooden box. A biscuit cannot escape a sealed tin, unless someone in the house is being suspiciously quiet. The world of objects is a world of boundaries. Even when something seems to pass through a barrier, there is usually a perfectly sensible explanation. Light passes through glass because glass is transparent to visible light. Sound passes through walls because vibrations travel through materials. Water seeps through a crack because the crack is there, however tiny and inconvenient. But if there is no opening, no hidden passage, no break in the barrier, then ordinary objects stop. They do not simply appear on the other side because the universe felt generous. That is the classical picture, the one that served science beautifully for a very long time. It is the world of clear paths and definite positions, where an object has a location, a speed, and a future you can predict if you know enough about it. Roll a ball up a hill without giving it enough energy, and it will slow, stop, and roll back. Throw a pebble at a wall without enough force to break it, and the pebble will not emerge from the other side looking pleased with itself. This kind of thinking works wonderfully for planets, pendulums, falling apples, and most of the things that make a noise when dropped on the kitchen floor. It is practical, sturdy, and reassuring, a bit like a well-made bookshelf. But when scientists began looking more closely at matter, when they peered into the atom and then deeper still, they found that the universe was not made of tiny clockwork pieces behaving in neat and obedient ways. The atom itself, once imagined almost like a miniature solar system, turned out to be much stranger. Electrons did not orbit the nucleus like planets around the sun. They existed in patterns, in states, in clouds of probability. The more closely physicists looked, the less the old picture of little hard particles on fixed tracks seemed to work. Matter was not quite solid in the way it appeared. Particles were not quite particles in the way pebbles are particles. Reality had a soft edge. This softness does not mean that your chair is about to become mist, or that your floor might suddenly decide to let you visit the downstairs neighbour without using the stairs. The everyday world remains wonderfully reliable because it is built from enormous numbers of quantum events averaged together into something stable. A wall is still a wall, a locked door is still inconvenient. But inside the quiet depths of matter, where individual particles meet barriers of energy rather than brick or plaster, something different can occur. A particle can encounter a barrier that, according to ordinary classical rules, should stop it completely. It may not have enough energy to cross over. It may not have enough energy to break through, and yet there remains a small chance that it will be found beyond the barrier anyway. That small chance is quantum tunneling. The name itself is a little misleading, though pleasantly dramatic. It makes it sound as if the particle has found a tiny shovel and is digging a passage beneath the obstacle, perhaps wearing a hard hat and whistling softly to itself. But there is no tunnel in the ordinary sense, no little corridor, no secret passageway lined with lanterns. The particle does not carve a route through the barrier. Instead, the mathematics of quantum mechanics tells us that the particle is described by something more spread out, more wave-like, and that this wave does not always stop sharply at the barrier. It can fade into it. It can extend through it. And if the barrier is thin enough, there can be a little of that wave on the far side. Where there is a wave, there is a chance of finding the particle, not a guarantee, not a promise. Just a chance, often a very small one, but real enough to shape stars, atoms, and technology. This is where quantum tunneling begins to feel less like a trick and more like a quiet feature of nature. The particle is not deciding to cheat. It is not sneaking through when the laws of physics are not looking. It is following different laws, ones that only become obvious when the things involved are extremely small. In the classical world, a barrier is a firm no. In the quantum world, a barrier is more like a very strong suggestion, usually obeyed, but not always. And that little not always is where the wonder lives. It helps to be careful here, because quantum tunneling is sometimes described in ways that make it sound like anything can pass through anything if you simply wait long enough. In one sense, quantum mechanics does assign tiny probabilities to very strange outcomes, but tiny really does mean tiny. The chance that all the particles making up a person could tunnel through a wall together is so unimaginably small that calling it unlikely feels far too generous, like calling the ocean slightly damp. For one particle, under the right conditions, tunneling is common and measurable. For a whole person made of vast numbers of particles, all needing to do something coordinated and absurdly improbable, the effect is not something you need to factor into your evening plans. You will not wake up halfway through the wardrobe because your atoms got adventurous, at least not for quantum reasons. Still, at the level of individual particles, the effect is not rare at all. It is part of the basic furniture of the microscopic world. In the heart of the sun, particles that would normally repel each other can get close enough, partly through tunneling, for nuclear fusion to occur. Without that, the sun would not shine in the same way, and mornings would be considerably less cheerful. In radioactive decay, particles trapped inside atomic nuclei can tunnel out, turning what looks like a sealed nuclear prison into something with a very strange escape clause. In scanning tunneling microscopes, electrons tunnel across a tiny gap, allowing scientists to map surfaces atom by atom, as though using probability itself as a fingertip. In electronics, tunneling can be both a useful tool and an annoying complication, especially as devices become smaller and smaller. The quantum world is not tucked away in some distant corner of theory. It is humming quietly inside the machinery of the modern age. There is something wonderfully humbling about that. We spend our lives in a world that seems solid and direct. We open doors, step over thresholds, carry keys, build walls, and trust surfaces to stay where they are. Then physics leans in and gently says that solidity is not quite what we thought. Matter is mostly space. Forces are doing the real work, and at small enough scales, the strict boundaries of the everyday world soften into probabilities. A particle does not have to behave like a tiny cricket ball. It can behave like a spread-out possibility, with just enough presence beyond the barrier that sometimes, when nature checks where it is, the answer comes back from the other side. That phrase, when nature checks, is not meant to suggest a person with a clipboard standing beside an atom, though honestly, physics would be easier if particles filled out forms. It points toward one of the stranger parts of quantum theory, the role of measurement. Before a particle is measured, quantum mechanics describes what can be known about it using a wave of probability. That wave may spread through space, overlap barriers, and extend into regions where classical physics would forbid the particle from being. When a measurement is made, we do not find a smear. We find the particle in one place. Sometimes, if the conditions allow, that place is on the far side of the barrier. The result is not magic, it is not a secret door. It is the outcome of a probability wave that did not end where common sense expected it to. Of course, common sense was never designed for this. Common sense was built for fruit, footsteps, weather, tools, family pets, and not walking into furniture in the dark. It is excellent for deciding whether a chair will hold your weight, or whether a soup bowl is too hot to lift without making a noise you will later deny. But it is not especially well suited to electrons, atomic nuclei, or the inner workings of stars. Asking common sense to understand quantum tunneling is a bit like asking a garden snail to review airport security procedures. It may have opinions, but the scale of the problem is not quite its natural habitat. So tonight, as we make our way into this topic, we will let common sense come along, but we will not put it in charge of the map. We will start with the familiar idea of barriers, because that is where the surprise begins. Then we will look at how the quantum particle differs from a little solid object. We will spend time with probability waves, because without them tunneling remains a magic trick rather than a physical process. After that, we will see how the impossible becomes not impossible, merely unlikely, and how unlikely events, given enough particles and enough time, can become extremely important. We will visit the centre of the sun, the inside of the atom, and the delicate instruments that let scientists feel the shape of matter on scales too small for the eye, or even imagination, to comfortably hold. And through it all, we will keep the pace gentle, no rushing, no need to force the mind through the wall. Quantum tunneling is already doing enough of that. Instead, we can let the idea unfold slowly, like steam rising from a cup in a quiet room. At first, it may look impossible. Then it becomes strange. Then, with a little patience, it becomes one of those ideas that still feels strange, but in a more familiar way. The way the moon feels strange if you stare at it long enough and remember that it is not a picture in the sky, but a world moving silently above the rooftops. Perhaps that is part of the comfort of physics. It does not always make the universe simpler, but it can make its strangeness feel less lonely. When you learn that particles can tunnel through barriers, you're not being asked to abandon reality. You're being invited to widen it. The wall remains, the particle remains, but the rules connecting them are more subtle than they first appeared. The universe is not careless. It is just quieter and more intricate than our everyday habits suggest. For now, keep hold of that ordinary image of a barrier, a wall, a hill, a locked door. Something that says, no farther. Something that separates here from there. Because in the classical world that no is firm, solid and dependable. It tells a ball to bounce back. It tells a traveller to find another path. It tells the world to stay organised. And before we can understand why the quantum world allows a different answer, we need to spend a little time with that familiar sturdy view, where walls are walls, particles are particles, and getting through anything always requires enough energy to do the job. To understand why quantum tunneling feels so strange, it helps to begin in the world where things behave themselves. The world of walls, doors, hills, fences, locked boxes, garden gates, and all the other stubborn objects that make everyday life predictable. This is the classical world, the one your hands and feet know very well. It is the world where a spoon stays in the drawer unless someone moves it, where a mug sits on the table until a regrettable elbow sends it somewhere less convenient, and where a wall, generally speaking, does not allow you through unless there is a door in it. Classical physics is the physics of common experience, and for most of what we do each day it works beautifully. It explains why a thrown ball follows an arc, why a bicycle rolls downhill, why a pendulum swings, why furniture resists being walked through, and why your socks do not spontaneously escape from a closed drawer, at least not in any way physics has yet been willing to admit. In this ordinary picture, objects have definite positions. A ball is here, not vaguely here-ish. A chair is in one corner, not politely considering several corners at once. If you walk across a room, you move along a path from one place to another. You do not vanish from the sofa and appear beside the kettle, unless you are in a film with suspicious editing. Every motion seems to involve a continuous journey. You start somewhere, pass through the space in between, and arrive somewhere else. That idea feels so obvious that we rarely notice it, but it is one of the deep habits of classical thinking. Things move through the world by following paths, and barriers interrupt those paths. A barrier, in classical physics, is anything that prevents motion unless the object has the right conditions to cross it. A wall is the most obvious example, but a barrier does not have to be made of bricks. A hill can be a barrier for a rolling ball. A locked door is a barrier for a tired person who left the keys in the wrong coat. A river can be a barrier to someone without a bridge. Even the rim of a bowl can be a barrier for a pea that would very much like to leave dinner early. What matters is not whether the barrier looks dramatic, but whether it stops something from going where it would otherwise go. Imagine a small ball rolling along a smooth floor toward a gentle ramp. If the ball is rolling quickly enough, it climbs the ramp, reaches the top, and rolls down the other side. If it is rolling too slowly, it climbs part of the way, slows down, pauses for a little moment of indecision, and then rolls back. Nothing mysterious happens. The ball does not reach halfway up the hill and then appear on the far side, perhaps looking smug. It either has enough energy to get over the barrier or it does not. In the classical world, that distinction is very clear. Enough means over, not enough means back. This is one of the simplest ways to picture a barrier in physics. A barrier is not always a solid thing. Sometimes it is a region that takes energy to cross. The ball on the hill needs enough motion to climb against gravity. A rocket needs enough speed to escape Earth. A car needs enough fuel to reach the top of a steep road without making that worrying noise drivers pretend not to hear. The exact details change, but the basic idea remains the same. To get past a barrier, an object must have enough energy to overcome what is resisting it. Walls are especially comforting examples because they are so direct. A wall does not need a lecture in mechanics to make its point. It simply stands there. If you toss a rubber ball at it, the ball bounces. If you roll a toy car into it, the car stops. If you lean your shoulder against it, the wall may creak slightly if it is an old house, but it does not normally say, "Come in." The reason is that the atoms in the wall resist the atoms in the ball, the car, or your shoulder. At the everyday scale, matter cannot simply pass through matter, because the electric forces between atoms push back. What feels like solid contact is really an enormous crowd of tiny electrical repulsions saying, "No thank you, this space is occupied." This is a useful little reminder because solidity itself is not quite what it appears to be. A wall feels solid because the particles in your hand are repelled by the particles in the wall. You're not actually experiencing two perfectly hard substances touching. In the way a simple cartoon might suggest, you are feeling forces. The electrons in the atoms of your hand and the electrons in the atoms of the wall do not wish to be squeezed into the same arrangement. They resist. That resistance becomes pressure. Pressure becomes touch. Touch becomes the very convincing experience of a surface. And so the wall feels solid, dependable, and entirely unwilling to let you drift through on your way to the kitchen. Classical physics handles this kind of situation very well. It treats objects as having definite shapes and positions. It treats forces as pushes and pulls. It describes motion as the result of those forces acting on objects over time. If the forces are strong enough in one direction, the object accelerates. If the wall pushes back harder than the ball can push through, the ball reverses direction. There is no hidden ambiguity. There is no maybe on the other side. There is only the clean logic of cause and effect, which is part of why classical physics feels so satisfying. It gives the world a firm outline. This way of thinking grew from centuries of observation. Long before the word classical was attached to physics, people knew that heavy stones required effort to lift, that arrows flew in curved paths, that carts were easier to pull on smooth roads, and that climbing over a wall was different from walking through one. The great achievement of classical mechanics was to turn these familiar patterns into precise descriptions. Isaac Newton, with his laws of motion and gravity, gave science a way to predict the movement of planets and projectiles, falling apples and ocean tides, pendulums and cannonballs. The universe became, for a while at least, a grand machine, and time was the steady ticking by which its gears could be understood. In Newton's world, if you know where an object is, how fast it is moving, what direction it is moving in, and what forces act on it, you can work out what happens next. That is a remarkable idea. It means the motion of a thrown stone is not random. The orbit of the moon is not a celestial whim. The swing of a clock pendulum is not a little act of household magic. Everything follows from conditions and forces. The future unfolds from the present in a way that can be calculated, at least in principle. This does not mean the calculations are always easy. Anyone who has tried to move a sofa through a narrow hallway knows that classical mechanics can still become emotionally complex. But the rules themselves are clear. Within that clear framework, barriers are not mysterious. They are simply arrangements of forces and energy. A wall resists because its structure holds together and pushes back. A hill resists because gravity must be overcome. A stretched rubber band resists because it wants to return to its relaxed shape. A spring resists compression. A sealed jar resists opening, sometimes more stubbornly than seems morally necessary. In each case, there is a condition that must be met. Apply enough force, provide enough energy, find the correct pathway, and the barrier can be crossed or broken. Fail to do so, and the object remains where it is, or returns from where it came. Picture again the ball rolling toward a hill. In classical physics, the hill has a kind of energy cost. The ball must spend its motion climbing upward. If it spends all its motion before reaching the top, it cannot continue. It has no secret reserve. It cannot borrow a little energy from a future version of itself. It cannot say, well, perhaps I will be found on the other side anyway. It rolls back. This is exactly the sort of situation that makes quantum tunneling surprising, because tunneling says that at the microscopic scale, under certain conditions, the particle does not always roll back. But before that can sound meaningful, we need to appreciate how firmly the classical world says it should. Think about trying to push a shopping trolley over a curb. If you push gently, the wheels bump and stop. If you push harder, the trolley rises and crosses. There is nothing personal about it, though it may feel personal if one wheel goes sideways and embarrasses you in front of the apples. The curb is a barrier. Your push supplies energy. The trolley either receives enough to cross or it does not. You could repeat the experiment many times, and if you keep the conditions the same, you expect the same result. That repeatability is part of the classical picture. Same object, same speed, same barrier, same outcome. The universe behaves like a patient instructor, demonstrating the same lesson over and over. Now imagine that sometimes, using the exact same trolley, the exact same curb, and the exact same tiny push, the trolley simply appears on the other side. Not because it jumped, not because the curb cracked, not because someone lifted it while you blinked. It just turns up beyond the obstacle. If that happened in a car park, people would gather. Someone would film it badly. A very serious person would say it was probably magnets. But at the quantum scale, something with that flavour really does happen. The difficulty is that we cannot import the shopping trolley version of common sense down into the atom and expect it to work. The classical view also depends on the idea that objects cannot be in forbidden regions if they lack the needed energy. Forbidden is a strong word, but it captures the feeling. A ball without enough energy cannot be at the top of the hill. A person without a ladder cannot stand on the roof by wishing. A stone cannot pass through a sealed wooden door unless it breaks it. The barrier divides what is accessible from what is inaccessible, and this division is sharp. Here is allowed. There is not allowed. The wall marks the boundary. This sharpness is one of the great comforts of the macroscopic world. You can place a book on a shelf and trust that it will not drift halfway into the plaster. You can close a cupboard and trust that the plates are inside, unless someone has stacked them in the strange household arrangement known as just putting things anywhere. You can shut a window and keep out the rain, because the rain cannot pass through intact glass like a ghostly visitor with poor manners. Classical barriers protect the structure of ordinary life. They make rooms possible. They make containers useful. They let us build houses, bridges, machines, and biscuit tins. Underneath all that familiar reliability is the behaviour of countless atoms. Each atom is governed by quantum rules, but when unimaginably many of them act together, the weirdness becomes averaged into solidity. It is a bit like hearing a crowd from far away. Individual voices may be unpredictable, but together they become a steady murmur. A wall contains such an immense number of particles that the chances of all of them behaving in a coordinated quantum strange way are effectively gone for practical purposes. A single particle can do something surprising. A wall made of trillions upon trillions of particles remains wonderfully boring, and in daily life boring is quite useful. You want your stairs to be classical. You want your teacup to be classical. You certainly want your chair to be classical, especially if you have already committed your full weight to it. Another important part of the classical view is that objects are localized. A tennis ball is not spread thinly through the room. It occupies a particular region. Its boundary may be fuzzy in a microscopic sense, because everything real has atoms and surfaces are not perfectly smooth. But for ordinary purposes, the ball is where the ball is. If it hits a wall, only the part of the ball touching the wall interacts directly with it. The rest of the ball follows because the ball holds together. The whole object behaves as one thing moving along one path. This is why it feels natural to talk about the ball approaching, hitting, bouncing, or stopping. A quantum particle, as we will soon see more clearly, is not so easily described. But in the classical picture, a particle is like a tiny bead. It has a place, it has a speed, it arrives at the barrier. If it has enough energy, it crosses. If it does not, it returns. That little bead picture is simple, tidy and deeply tempting, and even when people first learn about atoms, they often imagine electrons as specks circling a nucleus like bees around a hive or planets around a star. It is an understandable image, and for some purposes a useful stepping stone, but it is also exactly the kind of image that makes tunneling seem impossible. A bead cannot pass through an unbroken wall, a tiny marble cannot roll through a hill, a little planet cannot appear on the other side of an energy barrier if it never had enough energy to get there. The classical world also gives us a strong sense of separateness. Here and there are distinct. Inside and outside are distinct. Before and after are distinct. If you place a coin inside a box and close the lid, the coin remains inside unless the box is opened, broken, or tipped in some way that lets the coin out. The box is a boundary. We trust boundaries because we experience them constantly. Clothing separates us from cold air. Windows separate us from weather. Skin separates the body from the world around it. Roads separate lanes of traffic, though not always as persuasively as one might wish. Life is full of edges, and those edges shape how we think. That is why quantum tunneling can feel almost rude at first. It seems to violate the etiquette of boundaries. It suggests that a particle can be trapped and yet not fully trapped, blocked and yet not fully blocked, on one side and then sometimes on the other. But it only seems like a violation because the classical picture has taught us to expect a certain kind of story. Object approaches barrier. Object lacks energy. Object turns back. The quantum story begins with a different kind of object, or rather, a different description of what an object is. Still, the classical story is not wrong in its own domain. It would be a mistake to think quantum mechanics simply throws classical physics away. Classical physics is more like a beautifully accurate map of the world at human scales. It may not show every underground cave or microscopic stream, but for travelling across town, it is excellent. Engineers use classical principles to build bridges, pilots use them to fly aircraft, architects rely on them so ceilings do not become suggestions. Even when modern science uses deeper theories, classical physics often emerges as the practical approximation for large, slow, familiar things. It is not false, it is incomplete. And that incompleteness only shows itself when the world becomes very small, very fast, very cold, very energetic, or very precise. Quantum tunneling belongs to that small world, the one where the old assumptions begin to loosen. But if we do not first stand inside the old assumptions, we cannot appreciate why tunneling is so remarkable. The classical barrier says that an object either has the means to cross or it does not. There is no gentle fading into the barrier, no probability lingering beyond the wall. No chance of finding the object where it classically should never be. The rules are firm, and firm rules are useful. They keep bridges standing, clocks ticking, and soup inside bowls. Consider a marble in a bowl. If you roll it gently, it climbs the side a little and falls back to the bottom. Roll it harder, and it may reach the rim and escape onto the table, where it will immediately head for the least convenient place under the furniture. The rim of the bowl is a barrier. The marble must have enough energy to get over it. Without enough energy, it remains trapped. Classical physics can describe that motion in a way that feels almost story-like. The marble begins in the bowl, spends its motion climbing, loses speed, and returns. It is a little drama of effort and failure. Give it more motion, and the ending changes. But for the same starting conditions, the same result follows. Now shrink that idea down to an atomic nucleus holding a particle inside, or to an electron facing a tiny energy barrier in a solid material. The classical instinct says the same thing should happen. If the particle lacks enough energy to escape, it should stay trapped. If the electron lacks enough energy to cross, it should reflect back. But experiments show that microscopic particles do not always honour that expectation. This is not because the barrier is fake. The barrier is real. It is not because the particle secretly receives extra energy in the ordinary sense. It is because the quantum description of the particle is different from the classical bed picture. That difference changes what a barrier means. One reason this took so long for science to accept is that the classical picture is not merely intuitive, it is successful. It works again and again and again. It sends spacecraft to planets. It predicts eclipses. It explains machines. A theory that works that well earns our trust. So when the quantum world first began revealing itself, it did not simply add a few unusual facts. It challenged the habits of thought built from centuries of success, and from every ordinary experience of moving through a world of solid things. No wonder quantum mechanics still feels strange. It asks us to loosen the very ideas that helped us survive breakfast. Yet there is also something calming in seeing how the two views fit together. The classical world is not an illusion. Walls really do stop us. Barriers really do matter. Energy really is needed to cross hills, break doors, lift stones, and open jars that appear to have been sealed by a committee of mountain trolls. The quantum world does not erase any of that. It explains why, at the smallest scales, the firmness of barriers has another layer beneath it. What looks impossible in the classical description may become possible in the quantum one, not because anything goes, but because possibility itself is built into the structure of matter. So for the moment, let the wall remain solid. Let the rolling ball return from the hill. Let the marble stay in the bowl unless it is given enough motion to escape. Let the locked door keep its quiet authority. This is the world our senses understand, and it is the world classical physics describes with remarkable grace. It is a world of paths, forces, energy, and boundaries. A world where things are where they are, and barriers mean what they say. And now, with that sturdy picture in place, we can begin to soften it just a little, because the particle we meet next will not behave like a marble at all. It will be harder to pin down, less like a speck and more like a spread-out chance, and once that idea settles in, the wall will no longer look quite as absolute as it did before. Now that we have spent a little time in the reassuring world of classical barriers, where walls are walls and a marble without enough energy must roll back down the hill, we can begin to look more closely at the thing that changes everything, the particle itself. Because quantum tunneling does not begin with the wall, it begins with the strange nature of what is trying to cross it. If a particle were simply a tiny hard speck, like a grain of sand with a very serious schedule, then the classical picture would be enough. It would approach the barrier, fail to climb it, and return the way it came. No mystery, no tunneling, no need for anyone to pause their evening tea and reconsider the structure of reality. But a quantum particle is not a little marble in quite the way our imagination wants it to be. It is more elusive than that, more spread out, more difficult to pin down. Less like something rolling along a track, and more like a small cloud of possibility moving through the rules of nature. This is one of the first habits we have to loosen when we enter quantum mechanics. We like to picture small things as smaller versions of familiar things. A pebble is like a small rock. A grain of sugar is like a tiny crystal. A dust mote is like a little fleck floating in sunlight, usually just visible enough to make you wonder whether you should clean more often. So when someone says electron or proton, the mind naturally reaches for the same kind of image. It imagines a little bead, perhaps smooth and round, perhaps coloured in the helpful but misleading way school diagrams like to colour things. The electron becomes a tiny blue dot. The proton becomes a tiny red dot. They sit in the mind like pieces from a board game, neat and solid and easy to place. That picture is not useless. It can help at the beginning. It gives us something to hold on to while talking about things far too small to see. But it becomes misleading very quickly, because quantum particles do not behave like tiny balls that merely happen to be small. An electron is not just a miniature pea. A photon is not just a little pellet of light. A neutron is not a microscopic billiard ball waiting for someone with a very tiny cue. At the quantum scale, particles behave in ways that mix the qualities of objects and waves. They can arrive in one place when measured, yet before measurement they are described by a spread-out pattern of possibilities. They can act as if they travel along many possible routes, yet appear as a single detection on a screen. They are not vague because our instruments are poor. They are vague because nature itself gives them a different kind of existence. A helpful place to begin is with light. For centuries, scientists argued over whether light was made of particles or waves. Sometimes light behaves like a wave. It spreads out, bends around edges, and creates interference patterns, the kind of patterns you see when ripples on water overlap and make some regions stronger and others quieter. But light also behaves like particles, arriving in little packets of energy called photons. Shine a very dim light on a sensitive detector, and it does not arrive as a smooth smear. It arrives in tiny clicks, one photon at a time. So which is it? A wave or a particle? Quantum mechanics answers in the least convenient but most honest way. It is not exactly either in the familiar sense. It is something quantum, and our words wave and particle are borrowed from the large world because they are the best tools we have. Then the surprise deepened. It turned out that matter, not just light, has this same double nature. Electrons, which we often imagine as particles, can create interference patterns like waves. If you send electrons through a setup with two narrow openings, one electron at a time, each electron lands as a tiny point when it is detected. But after many electrons have arrived, the pattern they form is not the pattern of the little pellets simply passing through one opening or the other. It is the pattern of waves interfering. Somehow each electron is governed by a spread-out possibility that includes more than one route, even though the final detection is a single spot. This is not the behaviour of a marble. If you roll marbles through two gaps in a board, they make two piles. They do not quietly build a wave pattern while pretending to be sensible. This is why the idea of the quantum particle as a mist can be useful, as long as we do not take it too literally. A mist spreads through space. It does not have a sharp edge in the way a marble does. It can thin out gradually. It can drift into corners. But a quantum particle is not a physical fog made of little droplets. The electron is not smeared out because pieces of it are floating everywhere like steam from a kettle. Rather, what spreads out is the information about where it may be found. The quantum state gives a pattern of possibilities. Where the pattern is strong, the particle is more likely to be detected. Where the pattern is weak, it is less likely. When we finally measure it, we find the particle in one place. But before that measurement, the best description is not a tiny object with a secret exact path. It is a wave-like spread of possible outcomes. That is a very strange sentence, and it deserves to be allowed into the room slowly. A particle is found in one place when detected, yet before detection, it is described by a spread-out possibility. Our everyday minds want to ask where it really was before we looked. Was it here? Was it there? Was it sneaking behind the curtain with the air of someone who knows more than they are saying? Quantum mechanics does not give the old classical answer. It does not say the electron had a definite little root and we simply failed to observe it, at least not in the standard way the theory is used. It says the electron is described by a quantum state, and that state contains the probabilities for what we might find. The particle is not a marble with an unknown position. It is a quantum object whose position may not be definite until it is measured. This difference matters enormously for tunneling. In the classical picture, a marble reaches a wall and either goes over it or does not. But if the particle is described by a spread-out wave of possibility, then the barrier interacts with that wave. The wave can reach into the barrier, it can fade as it goes, it can become very small but not always vanish instantly, and if the barrier is thin enough, some of that wave can reach the other side. That small remaining presence beyond the barrier means there is a chance, sometimes small but real, that the particle will be detected there. The particle did not follow a normal path through the wall like a bead in a tunnel. The quantum description allowed a possibility to extend beyond where classical motion would have stopped. Before we go too far into that, let us stay with the particle itself. The word particle can be a little treacherous. It suggests a speck, a grain, a tiny piece of stuff with clear boundaries. But quantum particles are not like tiny crumbs from the biscuit tin. They are excitations of underlying fields, which is a more modern way of saying that what we call a particle is a localized event or disturbance in a deeper physical system. That may sound more complicated than calming, so we can keep it gentle. Think of a particle not as a permanent little bead, but as a way nature produces a definite interaction. When an electron is detected, it leaves a mark as one electron. When a photon is absorbed, it gives energy in one packet. These events are particle-like, but the behavior leading up to them is wave-like. This is sometimes called wave-particle duality, although the phrase can make it sound as if the particle is switching costumes backstage. Now I am a wave, now I am a particle. Very dramatic, very theatrical. But the reality is subtler. Quantum objects are not classical waves or classical particles. They are described by quantum rules, and depending on how we interact with them, different aspects become visible. If we set up an experiment to reveal interference, we see wave-like behavior. If we set up an experiment to detect impacts, we see particle-like behavior. The quantum object is not confused. We are the ones trying to describe it with words borrowed from waves in ponds and marbles on tables. One of the reasons quantum particles feel so slippery is that measurement changes the story. In everyday life, looking at something does not usually change where it is in any important way. You glance at a chair, and the chair does not leap into a new position out of embarrassment. You check whether your keys are on the table, and the act of checking does not normally fling them into the fruit bowl, although it may feel that way when you're late. But in the quantum world, measurement is not a passive glance. To measure a tiny particle, you must interact with it. You might bounce light off it, absorb it, scatter it, or make it trigger a detector. These interactions matter. They are part of the physical process. Quantum measurement is not simply discovering a pre-written answer hidden under a cushion. It is the moment when one possible outcome becomes the one we observe. This connects to another famous quantum idea, uncertainty. At the atomic scale, certain properties cannot both be known with unlimited precision. Position and motion, for example, are linked in a way that prevents us from giving a particle the same neat description we would give a tennis ball. This is not just because our rulers are clumsy. It is built into the structure of quantum behavior. If a particle has a very well-defined position, its motion becomes less well-defined. If its motion is very well-defined, its position spreads out. Nature does not hand us all the classical details at once. The particle is not sitting there with a complete little passport of exact information. waiting for us to read it more carefully. The limits are part of what it is. A marble does not behave like this. You can point to a marble and say it is there. You can watch it roll and measure its speed. You might not measure perfectly, because your eyes are tired or your equipment is cheap, or the cat has joined the experiment, but in principle the marble has a definite place and motion. The quantum particle resists that kind of complete description. It is not merely hard to observe. It is not classical underneath in a simple way. Its state is more like a set of possibilities with rules for how those possibilities change and how likely different outcomes are. That is why comparing it to mist helps. Not because the particle is made of mist, but because mist reminds us not to expect sharp edges and one tidy path. Imagine a patch of fog in a field. If you ask exactly where the fog is, the answer is not a single point. It is spread out. It may be thicker in one place and thinner in another. It may fade gradually rather than stop at a clean boundary. A quantum probability pattern has a little of that quality. There are regions where the particle is likely to be found, regions where it is unlikely, and regions where the possibility becomes so tiny that for practical purposes we can ignore it. But tiny is not the same as zero. This distinction, quiet as it sounds, is the doorway to tunnelling. A classical marble either reaches a region or it does not. A quantum state can fade into a region where the particle would not classically have enough energy to go. Now it is worth being careful with the word probability. In ordinary life, probability often means ignorance. If I say there is probably a biscuit left in the tin, what I really mean is that I have not checked and I am maintaining hope. The biscuit is either there or not. My uncertainty is about my knowledge, not about the biscuit itself. Quantum probability is deeper than that. It is not simply that the particle has a definite hidden location, and we are ignorant of it. The probability pattern is part of the physical description. It can interfere with itself, it can spread, it can change, it can produce results that could not be explained by ordinary ignorance alone. This is why electrons in the two-opening experiment form interference patterns even when sent one at a time. Each electron is not merely choosing a path like a tiny indecisive commuter. Its quantum state includes possibilities that combine like waves. The idea of interference is especially important, though we do not need to make it technical. Think of ripples on a pond. When two ripples meet, they can reinforce each other in some places and cancel each other in others. A similar kind of pattern appears in quantum experiments, except what is interfering is not water height, but probability. In some places, the chance of finding the particle becomes greater. In others, it becomes smaller. This is deeply unlike a marble. Two possible routes for a marble do not cancel each other out. If you walk to the kitchen by one route or another, you do not arrive less because the routes interfered, though you may arrive later if you stop to wonder why you went there in the first place. This wave-like behaviour is not just a laboratory curiosity. It is one of the core reasons atoms exist as they do. Electrons in atoms do not spiral into the nucleus like tiny planets losing energy. Instead, they occupy quantum states, patterns around the nucleus that determine how atoms bond, glow, absorb light, and build the chemistry of everything from salt to trees to sleepy human brains listening to science at night. The solidity of the world, the colours of materials, the structure of molecules, and the behaviour of metals all depend on the fact that particles are quantum objects, not classical marbles. The same strangeness that allows tunnelling also allows matter to have the rich structure we depend on every moment. At this point, it may be tempting to imagine that quantum particles are somehow unreal until measured, like actors waiting for the stage lights. That can be a misleading picture too. They are very real. Electrons carry charge. They push and pull. They shape atoms. They flow through wires. They create magnetic effects. They are not imaginary. But their reality does not match the tidy categories we use for familiar objects. The electron is real, but not like a pea. A photon is real, but not like a tiny glowing grain. The quantum particle asks us to accept that reality can be definite in its effects, while still being described by possibilities before those effects appear. This is a gentle but important shift. We're not saying the particle is literally everywhere in the universe in a useful sense. We're not saying it can do absolutely anything. Quantum behavior is not a license for chaos. The possibilities follow strict rules. Some outcomes are likely, some are unlikely. Some are so unlikely that the universe may as well have locked them in a cupboard and misplaced the key. The quantum world is strange, but it is not random nonsense. It has order, structure, and patterns that can be measured with extraordinary precision. Its oddness is disciplined oddness, which is perhaps the most physics kind of oddness there is. So when we say a particle is more like a mist than a marble, we are trying to loosen the imagination without losing the science. The marble has a clear location, a clear path, and a clear boundary. The quantum particle has a state that may be spread out, a set of possible detections, and a wave-like behavior that can interact with barriers in a way no marble can. The marble either strikes the wall or crosses only if it has enough energy. The quantum particle brings with it a probability pattern that may seep into the barrier and, under the right conditions, leave a faint possibility beyond it. That faint possibility is not decorative. It is enough for real tunneling to occur. Notice how slowly the wall has begun to change, even though the wall itself has not moved. We have not made the barrier weaker. We have not added a secret hole. We have not given the particle a tiny ladder. We have only changed our picture of the particle, and that is already enough to make the classical story less complete. A marble meets a barrier from one place at a time. A quantum particle, through its probability wave, can have a presence that reaches into the region of the barrier. It does not need to be imagined as a little object forcing its way through brick. It is better to think of the quantum state as something that can extend, fade, and continue, even where classical motion would have ended. There is a quiet lesson in this. Sometimes the strangeness of nature does not come from adding something dramatic. It comes from realizing that a familiar word was carrying too much baggage. Particle sounds simple. Wall sounds simple. Through sounds simple, put them together, and the phrase particle goes through a wall sounds like a magic trick. But each word changes meaning at the quantum scale. The particle is not a marble. The wall is often an energy barrier rather than a brick one. And going through does not mean carving a classical path from one side to the other. It means the particle has some probability of being found beyond a barrier that classical physics would not allow it to cross. That is why the next step is to look more carefully at the probability wave itself, not as a decorative idea, not as a metaphor floating gently around the particle, but as the central description that makes tunneling possible. The particle we have been imagining is not a little bead with a fog machine. It is a quantum object whose possible location is described by a wave-like pattern. That pattern can spread, overlap, shrink, and persist. It can meet a barrier and not simply stop dead at the edge. And once that becomes clear, the question of tunneling changes from how can a marble pass through a wall to what happens when a wave of possibility meets a region it is unlikely but not entirely forbidden to cross. The strange thing about a probability wave is that it asks us to change the kind of picture we carry in our minds. We're used to thinking of a thing as being somewhere, not spread across possibility, not waiting to become definite, not described by a pattern that tells us where it might be found. Just somewhere. Your cup is on the table, your pillow is on the bed, your keys are either in your pocket, on the counter, or, in the grand tradition of keys everywhere, in a place that makes no sense at all. But even when you do not know where the keys are, you still believe they are in one definite location. They are not softly distributed through several rooms as a haze of potential inconvenience. They are somewhere. You're simply not yet aware of where. Quantum particles make this familiar way of thinking much less comfortable. When we talk about an electron or a proton or a photon of light, we're not simply talking about a tiny object whose exact location is hidden from us because our tools are clumsy. We are talking about something that nature itself describes in terms of possible outcomes, The probability wave is the way quantum mechanics keeps track of those outcomes. It is not a wave of water, not a wave of air, and not a little physical ripple waving hello as it travels through space. It is a pattern that tells us where a particle may be found, and how likely those findings are. Where the pattern is strong, detection is more likely. Where the pattern is faint, detection is less likely. And where the pattern reaches, possibility reaches with it. This is already very different from a marble. A marble does not need a probability wave to tell us where it might be, unless perhaps it has rolled under the sofa and joined the mysterious civilization of lost household objects. A marble has a position whether or not we are looking. It follows a path, even if we did not see the path. It may be hidden, but it is not undecided in the quantum sense. A particle, however, is not described completely by saying that it has a little hidden route. Before measurement, the quantum description spreads out. It contains a range of possible places where the particle could appear. Then when the particle is detected, the result is definite. One dot on a screen, one click in a detector, one tiny interaction in one location. The miss becomes a point, so to speak, though even that phrase should be held gently. One reason this idea feels so odd is that we often confuse probability with ignorance. In ordinary life, probability is usually about what we do not know. If you toss a coin and cover it with your hand, you might say there is a chance it is heads and a chance it is tails. But the coin itself has already landed. It is not both in any mysterious sense. Your uncertainty belongs to you, not to the coin. The coin is simply waiting for you to lift your hand and discover what happened. That kind of probability is familiar. It is the probability of weather forecasts, misplaced glasses, late buses, and whether there is enough milk left for tea. Quantum probability is not like that. Or at least, it is not merely like that. It is not just a polite way of saying that the particle has a secret position and we have not found it yet. The probability wave behaves physically in ways that ordinary ignorance cannot explain. It can spread, it can overlap with itself, it can create patterns of stronger and weaker likelihood, it can pass through openings and produce interference, the unmistakable sign of wave-like behavior. If quantum probability were only a matter of not knowing enough, these patterns would not appear in the same way. Something deeper is happening. The particle is not carrying a little sealed envelope with its true path written inside. Nature seems to be using possibility as part of the machinery. This becomes clearer when we think again about waves, but carefully. A wave on a pond is a movement of water. A sound wave is a movement of air or another material carrying pressure changes from place to place. A light wave is more subtle, involving changing electric and magnetic fields. But a probability wave is not a substance being waved up and down. It is not made of tiny droplets. It does not splash. It will not make your socks damp. It is a mathematical and physical description of what may happen when a quantum system is measured. That sounds a little dry, but it is one of the most powerful ideas in science. It lets us predict how atoms absorb light, how electrons move in materials, how chemical bonds form, and how tunneling can occur. Let us make it more comfortable with an image. Imagine standing in a dark room with a small lamp covered by a soft shade. The light is brightest near the lamp, and it grows dimmer as you move away. If you were told that a tiny moth was more likely to be found where the light is brighter, and less likely where the light is faint, the brightness could act as a guide to probability. It would not be the moth itself spread around the room. It would be a pattern telling you where the moth is more likely to appear. A probability wave is not the same as lamplight, of course, but the image helps us separate the particle from the pattern. The particle is detected in one place. The pattern tells us the chances of where that place may be. Now imagine that this pattern does not have a hard edge. It fades. It thins. It may become extremely weak but not always vanish abruptly. This is important. In the ordinary world, an object often seems to have a boundary. A ball ends at its surface. A table ends at its edge. A biscuit ends when someone says they will only have half and then quietly revises the plan. But the probability wave can have a tail. It can stretch into regions where the particle is unlikely to be found. Most of the chance may be concentrated in one area, but a little chance may extend outward. That faint extension may sound unimportant, yet in quantum mechanics, faint does not mean meaningless. If the chance is not zero, then under the right conditions the event can happen. This is where the idea begins to lean toward tunneling. When a quantum particle approaches a barrier, the probability wave does not behave like a marble striking a wall. A marble meets the wall at its surface. If it cannot break through or climb over, it bounces back. The marble does not partly enter the wall as a fading possibility, but a probability wave can reach the barrier and extend into it. Inside the barrier, the wave often fades quickly. The barrier suppresses the possibility. It makes the chance smaller and smaller. But if the barrier is not too thick, a tiny part of the wave may still exist on the far side. Once there is a tiny part of the probability wave on the other side, there is a tiny chance of detecting the particle there. Not because the particle smashed through, not because it borrowed energy from a little quantum bank with alarming interest rates, because its quantum description allowed the possibility to reach beyond the barrier. It may help to think of the barrier not as a brick wall at first, but as a region that is difficult for the particle to occupy. In many tunneling situations, the barrier is an energy barrier. It is not always a physical slab of material like the wall of a bedroom. It is a region where, according to classical physics, the particle does not have enough energy to be. The particle should turn back. But the probability wave can extend into that classically forbidden region. That phrase sounds dramatic, as if the particle is sneaking through a velvet rope at a very exclusive nightclub, but it simply means that classical motion would not allow the particle there. Quantum mechanics says the possibility can still fade into it. The fading is crucial. Tunneling is not a free pass through anything. A thick barrier makes the probability wave shrink so much that the chance of appearing on the other side may become practically zero. A high barrier also suppresses the chance strongly. This is why you do not see tennis balls tunneling through doors or people accidentally emerging from the far side of a hill after a brisk walk. At large scales, the probability becomes so fantastically tiny that it has no practical role in everyday life. But for electrons, protons, and other tiny particles, especially when the barriers are extremely thin, the effect can be very real. Small scales are where the faint tails of probability still matter. There is another useful picture, though again we must not stretch it too far. Imagine a sound coming from the next room. If the wall is thick, you may hear almost nothing. If the wall is thin, a little sound comes through. The sound has not knocked down the wall. It has not opened the door. It has simply extended through the material in a weakened form. A probability wave is not a sound wave, but the comparison helps with the idea of fading rather than stopping sharply. Classical objects tend to make us imagine all or nothing. The wave picture allows for gradual weakening. A little presence remains, and in quantum mechanics, a little presence can mean a measurable chance. The probability wave also explains why repeated experiments with identical particles do not always produce the same individual result. In the classical world, if you roll the same ball toward the same hill with the same speed, you expect the same outcome every time. If the ball lacks the energy to get over, it rolls back every time. But if you send many identical quantum particles toward a barrier, some may reflect and some may tunnel. You cannot usually predict which single particle will make it through. You can predict the overall pattern. Out of many trials, a certain fraction may appear on the far side depending on the barrier and the particle. Quantum mechanics is not careless. It gives reliable probabilities, but it does not always give the old classical certainty for each individual event. That distinction is important because it keeps us from thinking of tunneling as a tiny mechanical trick. It is not that some particles find invisible cracks while others fail to notice them. It is not that the successful ones were secretly stronger. If the particles are prepared in the same way, quantum mechanics may still only allow a probability of transmission. The wave meets the barrier. Part of the probability is reflected. Part may continue beyond. When a measurement is made, the particle is found either on one side or the other. The result is individual. The pattern is statistical. This is one of the places where quantum physics feels both precise and deeply unlike ordinary experience. The word spread is also worth treating gently. When we say the particle spreads into possibility, we are not saying that the particle is physically smeared out like butter over toast, though that is a pleasant image and now perhaps a slightly distracting one. We mean that the quantum state can occupy a range of possible positions. The particle, when detected, appears whole. An electron does not arrive as half an electron in one place and half an electron in another. Detectors register complete particles, but the probability of where the particle may be found can be spread out before detection. The spread belongs to the quantum description, not to a chopped-up particle. This is why the language of quantum mechanics can feel so slippery. If we say the electron is a wave, that is not quite right. If we say it is a particle, that is not quite right either. If we say it is a probability wave, that is closer, but still easy to misunderstand. The electron is a quantum object. It behaves according to quantum rules. The probability wave is our way of describing its possible measurement outcomes and how those possibilities evolve. The trouble is that our brains prefer furniture. They prefer things that sit still, have edges, and do not require a careful explanation before becoming visible. Quantum particles are not furniture. They are more like the rules beneath the furniture, the quiet instructions out of which solid things eventually arise. One of the most famous demonstrations of this is the experiment with two narrow openings. When electrons are sent one at a time toward a screen with two openings, each electron is detected as a single spot beyond the screen. If electrons were merely tiny pellets, the final pattern would look like two blurred piles, one behind each opening. But that is not what happens. Over time, the spots build up into an interference pattern, a pattern associated with waves. It is as though the probability wave passes through both openings and combines with itself before the electron is detected. Yet each detection is one electron in one place. The result is not easy to picture, but it is not optional. It is what experiments show. This tells us something profound. A quantum particle cannot always be described as taking one definite route before measurement. The probability wave may include several possibilities at once, and those possibilities can affect each other. In everyday life, possible routes do not interfere. If you are deciding whether to walk to the shop by the park or by the main road, the route you do not take does not cancel out the route you do take, unless perhaps you become distracted and go home instead. In quantum mechanics, alternatives can combine in wave-like ways. This is why probabilities are not just a bookkeeping tool. They have structure. They can overlap, reinforce, and reduce one another. When this structured probability meets a barrier, the result is tunneling. Not always, and not dramatically at human scales, but often enough at microscopic scales to be essential. The probability wave does not simply stop at the point where classical physics says no. It changes shape. It enters the barrier in a weakened form. It may decay so rapidly that almost nothing reaches the far side. Or, if the barrier is thin, enough remains for a measurable chance. That chance may be small, but nature is very patient with small chances. In a sample with countless particles, even a small probability can lead to many events. A single unlikely tunneling event may be rare. A vast number of particles trying again and again can make tunneling a steady process. This is especially important in the Sun, where charged particles repel one another. Classically, many of them would not have enough energy to get close enough to fuse. The barrier created by their electrical repulsion should stop them. But the particles are quantum objects. Their probability waves can overlap in ways that allow fusion to happen more often than classical physics alone would permit. The Sun does not rely on particles politely climbing over every barrier by ordinary means. It relies in part on tunneling. That quiet quantum allowance helps sunlight exist. The warmth on your face, the glow through a window, the energy stored in plants and food, all of it is connected to tiny probabilities in the hearts of stars. Not a bad result for something that sounds at first like a loophole. In radioactive decay, the same idea appears in another setting. Some particles are held inside atomic nuclei by powerful forces, yet there may be a chance for them to tunnel out through an energy barrier. Classically, they are trapped. Quantum mechanically, their probability wave extends beyond the barrier just enough that escape can occur. We cannot usually say exactly when one particular atom will decay, but we can predict how a large collection will behave over time. Again, the individual event is uncertain. The pattern is reliable. This is quantum probability doing its quiet work, making the unpredictable statistically dependable, which is rather like a very strange clock that refuses to tell you when one tick will happen, but tells you very accurately how many ticks to expect from a crowd of clocks. There is a comfort in that reliability. Quantum mechanics may be strange, but it is not a shrug. It does not say anything can happen for no reason. It says certain things can happen with certain probabilities, and those probabilities follow exact rules. The probability wave is not a decorative mist of maybe. It is a disciplined pattern. It evolves in a consistent way. It responds to barriers, forces, and conditions. It allows scientists to build technologies with astonishing precision. If the quantum world were merely random in the casual sense, modern electronics would not work, lasers would not work, atomic clocks would not work. The devices around us depend on the fact that quantum probability is strange, but dependable. Another way to understand the probability wave is to think about how it guides expectation without choosing an outcome in advance. Suppose you scatter many seeds across a garden bed according to some careful pattern. One seed may land here, another there, but after many seeds, the overall shape becomes clear. A probability wave is not a hand throwing seeds, but repeated quantum experiments have that quality. Each detection is individual. Many detections reveal the pattern. If the wave is strong in one region, many particles will be found there. If it is weak in another, only a few. The pattern is invisible in a single event, but clear in the collection. Quantum mechanics often reveals itself not through one dramatic occurrence, but through patience, repetition, and statistics, which is less flashy than a magic show but considerably more useful. Still, when we speak of a particle spreading into possibility, we should not imagine that anything goes. The probability wave does not spread however it likes. It depends on the particle, its energy, and the environment around it. Boundaries affect it. Forces affect it. Barriers affect it. In atoms, probability waves form stable patterns around nuclei. In materials, electrons occupy allowed states shaped by the structure of the solid. In tunneling, the barrier reshapes the wave and determines how much possibility survives on the far side. This is why different barriers produce different tunneling probabilities. A thinner barrier is easier to tunnel through. A lower barrier is easier. A particle with more suitable energy has a better chance. The details matter, even though we are avoiding equations and letting the ideas stay verbal. It is also helpful to remember that probability waves are not unique to exotic laboratories. They are part of every bit of matter. The reason we do not notice them directly is that large objects have quantum states that become extraordinarily localized and tangled with their surroundings. A dust grain, a spoon, or a person interacts constantly with air molecules, light, heat, and everything nearby. These interactions destroy the delicate, spread-out behavior we associate with isolated quantum particles. The result is that large objects behave classically. They have stable positions. They do not show obvious interference. Their tunneling chances through ordinary walls are effectively non-existent. The quantum miss becomes, for all practical purposes, a marble again. That phrase, for all practical purposes, is doing a lot of work. At the deepest level, the world remains quantum. But the classical world emerges because the quantum possibilities of large objects are overwhelmingly constrained by their size, their mass, and their constant interactions with the environment. This is why quantum weirdness is not visible in your living room unless your living room contains a physics department, which may be its own kind of barrier to relaxation. The small world is delicate. It requires isolation, precision, and tiny scales for its odd behaviour to stand out. Otherwise, the weirdness averages away, leaving chairs, walls, and the dependable refusal of tables to let cups pass through them. As we move toward tunnelling itself, the central idea to keep is simple, though not ordinary. A quantum particle is described by a probability wave. That wave gives the chances of where the particle may be found. It can spread out, it can fade, it can enter regions that classical physics would forbid. If a barrier is thin enough, some of the probability wave can reach beyond it, and if the wave reaches beyond it, then there is a real chance that the particle will be detected there. The particle has not broken the rules. It has followed quantum rules rather than classical ones. This changes the question in a gentle but important way. We no longer ask how a tiny marble punches through a wall without enough energy. That question belongs to the wrong picture. Instead, we ask how a spread-out quantum possibility behaves when it meets a barrier. Does it vanish at the edge, or does it fade into the barrier? Does any of it remain beyond the barrier? How likely is detection on the other side? These are the questions that make tunnelling understandable, not familiar exactly. Quantum mechanics rarely becomes familiar in the way a kettle or a lamp becomes familiar. But it can become less bewildering. The wall is still there. The particle is still real. The difference is that possibility has a shape, and that shape does not always stop where our everyday instincts expect it to. So let the image settle for a moment. Not a marble, hard and small, striking a wall and bouncing back. Not a ghost passing through bricks with theatrical ease, but a quantum particle described by a probability wave, strongest where it is most likely to be found, fading where it is less likely, and sometimes extending just far enough beyond a barrier for the impossible to become merely unlikely. Once that is in place, tunnelling is no longer a violation of nature. It is nature doing what its smallest rules allow. And from here we can begin to watch the process itself, the moment when a barrier that should stop everything becomes, for a quantum particle, not an ending but a very narrow possibility. Now we can bring the particle and the barrier together and watch the odd little event begin. Not with a crash, not with a sparkle, not with the sort of dramatic sound effect cinema might add if an electron were given its own heroic entrance, but with something much quieter. A quantum particle approaches a barrier it should not be able to cross. Classical physics looks at the situation, checks the energy, checks the obstacle, and gives a firm answer. The particle cannot pass. It does not have enough energy. It must turn back. That would be the whole story in the ordinary world, and a very sensible story it would be. But quantum mechanics does not stop at the classical answer. It asks what happens to the probability wave, and that is where the impossible begins to soften. Picture again the familiar hill. A ball rolls toward it with too little energy to reach the top. It climbs part of the way, slows down, pauses and rolls back. We understand that. We can almost feel the motion in our hands. The ball does not vanish halfway up and appear on the far side. It does not decide that the hill is more of a suggestion than a landscape feature. It cannot be where its energy does not allow it to be. In the classical picture, the hill draws a clean boundary between what can happen and what cannot. The ball may climb only so far. Beyond that point, no. A quantum particle facing an energy barrier is not a rolling ball. We have been letting that idea settle slowly. The particle is described by a probability wave, a spread of possible places where it may be detected. When that wave reaches the barrier, it does not simply slap against it and stop like a wet towel on a window. It changes. Part of it is reflected, which means there is still a chance the particle will be found back on the side it came from, but part of the wave can extend into the barrier. Inside the barrier, the wave fades. It becomes weaker and weaker as it moves through the region that classical physics would forbid. If the barrier is too thick, the fading becomes so extreme that nothing useful reaches the far side. But if the barrier is thin enough, a tiny amount of the wave can emerge beyond it. And where the wave exists, however faintly, there is a chance of finding the particle. That is tunneling. It is not the particle digging through the barrier. It is not the particle secretly having more energy than we thought. It is not a tiny act of rebellion by matter. It is the probability wave extending into and through a region that classical motion cannot enter. When a measurement is later made, the particle may be found on the far side. From an everyday point of view, it looks as if the particle has passed through the wall. From the quantum point of view, the wave never ended sharply at the wall in the first place. It faded, persisted, and left a small chance beyond the barrier. This is why the phrase quantum tunneling can be both useful and misleading. Useful because it gives us a simple image. Something is on one side of a barrier, and later it is on the other side, even though it did not have the classical energy to cross. Misleading because it makes us imagine a route, a passage, a little hidden corridor. The word tunneling belongs to miners, moles, railway engineers, and perhaps people trying to avoid awkward conversations at parties. But a quantum particle does not make a tunnel in the barrier. It does not travel through a narrow tube. The barrier remains intact. What passes through, in a sense, is the possibility of detection, weakened but not always destroyed. Imagine placing your hand against a wall. Your hand stops. That is that. The wall and your hand are both made of enormous numbers of particles, all interacting, all producing the stable, classical behavior we rely on. Now imagine a single electron approaching a very thin energy barrier inside a material. The electron is not a little hand. The barrier is not a brick wall. The conditions are delicate, microscopic, and governed by quantum rules. The electron wave can extend into the barrier and sometimes beyond it. If the barrier is narrow enough, the electron may be detected on the other side. At that scale, the word impossible has to be replaced by something more careful. Not forbidden absolutely, just unlikely. This replacement is one of the great shifts in quantum thinking. Classical physics often gives yes or no answers. Enough energy, yes. Not enough energy, no. Quantum mechanics often gives chances. More likely here, less likely there. Very unlikely beyond the barrier, but not always impossible. In ordinary language, unlikely and impossible can feel close together when the chance is tiny enough. If someone says it is unlikely that a teapot will float gently through the ceiling tonight, you might reasonably treat that as impossible and go on with your evening. But in physics, the difference matters. A chance can be tiny and still be real, and if enough particles try enough times under the right conditions, tiny chances can become steady, measurable effects. This is one of the reasons tunneling matters so much. A single tunneling event may seem like a rare little exception, but nature does not work with just one particle. It works with crowds beyond counting. In a piece of material, countless electrons are moving and interacting. In a radioactive sample, countless nuclei sit with particles confined inside them. In the center of a star, vast numbers of protons move in the hot, dense plasma. Even if each individual chance is small, the number of attempts is enormous. Given enough trials, unlikely does not stay hidden. It becomes a process. It becomes heat, light, decay, current, signal, structure. The small chance becomes part of the large world. Let us stay with the barrier for a moment. In tunneling, two things are especially important: how high the barrier is and how wide it is. High and wide are everyday words, but here they refer to how difficult the barrier is for the particle to cross. A barrier that is very difficult makes the probability wave fade quickly. A barrier that is wide gives the wave more distance over which to fade. If the wave fades almost completely before reaching the far side, tunneling becomes extremely unlikely. If the barrier is thin, some of the wave may survive. Then the particle has a better chance of being found beyond it. This gives tunneling a very practical character. It is not random in the casual sense. Change the thickness of the barrier and the chance changes. Change the particle energy and the chance changes. Change the shape of the barrier and the chance changes. Scientists can measure these changes. Engineers can use them. Tunneling is strange, but it is not vague. It follows rules so reliably that modern devices can be built around it. This is often the pattern with quantum mechanics. It begins by making common sense feel underdressed, and then, just when you wonder whether reality has become too slippery, it turns out to be accurate enough to build instruments of remarkable precision. A helpful way to think about the fading wave is to imagine a smell drifting through a closed door. Not because a probability wave is a smell, of course. No electron has ever politely scented a hallway with lavender. But the image helps with the idea of weakening. If someone is baking bread in another room, a little scent might reach you even though the door is shut. The smell is weaker than it would be with the door open. It fades with distance. A thick door blocks more than a thin one. Again, this is only an analogy. A probability wave is not made of air molecules, but it helps loosen the all-or-nothing expectation. Some things do not stop sharply, they fade, and if enough remains on the other side, something can be detected. The difference is that with tunneling, what remains is not a faint physical substance leaking through a crack. It is the mathematical possibility of finding a particle beyond the barrier. That possibility is not imaginary. It can produce real detections, real currents, real nuclear decays. This is why quantum mechanics can be so difficult to explain in ordinary language. The probability wave is not a material cloud, yet it is not merely a guess in someone's notebook. It is a physical description with consequences. It tells us what can happen, and tunneling is one of the things it allows. Now, if you're wondering whether the particle spends time inside the barrier, you have wandered into a very subtle part of the subject. Physicists have thought deeply about questions like that. How long does tunneling take? What path, if any, does the particle follow? Can we speak of it being inside the barrier at all? These are not simple questions, because the classical idea of a path is exactly what starts to fail. In many practical situations, it is better not to imagine the particle as a tiny object moving through the barrier step by step. The quantum description tells us about the state before, the state after, and the probabilities connecting them. Trying to insert a little classical movie in between can create more confusion than clarity, rather like trying to explain a dream using a street map. Still, for a gentle evening journey, we can keep the main idea steady. Before measurement, the particle is described by a wave of possibility. The barrier makes that wave shrink inside it. Sometimes the wave reaches the far side. Then there is a chance of detection there. That is enough to understand why tunneling is not magic. It is not an object breaking a rule. It is the rule itself being different from the one our everyday experiences taught us. A classic example often used in teaching is an electron approaching a thin barrier in a solid. Imagine the electron is confined on one side. Classically, it lacks the energy to cross. If it were a marble, the story would end. But because it is quantum, its wave extends into the barrier. If the barrier is very thin, the wave can extend beyond it. A detector on the far side may register the electron. It appears as a complete electron, not as a smear, not as a tired little fraction of itself, but as one particle. The probability was spread out. The detection is definite. This is one of the recurring rhythms of quantum mechanics. Possibility spreads, measurement selects. That phrase may sound a little too tidy, so let us ground it. Suppose scientists prepare many electrons in the same way, and send them toward the same barrier. They may find that most reflect back, while a small fraction appear beyond the barrier. They cannot usually say in advance which exact electron will tunnel. but they can predict the overall fraction with great accuracy. If they make the barrier thicker, fewer electrons tunnel. If they make it thinner, more do. This is not superstition. It is measurement. It is repeatable. The barrier is not being fooled. The particles are not taking turns out of politeness. The pattern comes from the probability wave. This also explains why tunneling does not mean a particle can cross any barrier with equal ease. Sometimes popular descriptions make quantum mechanics sound like a universe where everything is allowed if you wait long enough. That can be entertaining, but it misses the discipline of the theory. A particle has a tunneling chance only under specific conditions, and that chance may become so small that it has no practical meaning. The larger the object, the thicker the barrier, and the more strongly the system interacts with its surroundings, the less visible tunneling becomes. By the time we reach the scale of people, walls, and furniture, the effect has faded beyond relevance. The world returns to classical behaviour, which is why your front door remains useful, and why bedrooms do not need warning labels about quantum leakage. There is something almost amusing about the contrast. For an electron, a barrier may be negotiable. For a person, it is a wall. This is not because the electron is more determined. It is not because the person has poor quantum technique. It is because the quantum wave nature of large objects is so tightly constrained, so thoroughly tangled with the environment, and so incredibly unlikely to produce coordinated tunneling that the effect disappears from ordinary life. Every particle in a person would have to tunnel in a coordinated way for the person to appear on the other side of a wall. The probability is so small that it is not worth treating as a real possibility. You're much better off using the door, even if it is a little squeaky. At the microscopic scale, though, tunneling can be ordinary. Not ordinary in the sense of boring, but ordinary in the sense of happening all the time. It is part of how particles behave near barriers. It is not a rare loophole in the laws of physics. It is a consequence of the laws. The reason it surprises us is that our senses are built from the large-scale result, not the tiny underlying behaviour. We live in the averaged world. We feel the wall, not the electron probability waves. We see the lamp, not the quantum transitions that allow light and matter to interact. We feel warmth from sunlight, not the tunneling events deep in the sun that help make that light possible. Quantum tunneling is hidden from ordinary sight, but not absent from ordinary life. The phrase classically forbidden is often used for the region inside the barrier. It sounds severe, as though nature has placed a stern sign there telling particles to keep off the grass. In classical mechanics, the particle cannot be in that region because it does not have the required energy, but in quantum mechanics, the wave can extend there in a fading form. The particle is unlikely to be found there, and if the barrier is thick enough, almost impossibly unlikely to be found beyond it. But the word forbidden no longer means absolutely impossible. It means forbidden by classical rules, not by quantum rules. This is a good example of how physics evolves without simply throwing away what came before. The classical view is still useful. It gives the correct result for large objects and many everyday situations. But quantum mechanics reveals that the classical view is an approximation, a simplified picture that emerges when probabilities become so sharply concentrated that objects seem to follow definite paths. At small scales, the fuller picture appears. A barrier is not merely a stop sign. It is something that reshapes the probability wave. Most of the time it reflects. Sometimes it transmits. The particle may be found where the classical story said it should not be. There is a quiet beauty in the fact that this tiny effect can have such large consequences. If tunneling were just a strange laboratory trick, it would still be fascinating. But it is far more than that. It helps explain radioactive decay, where particles escape from nuclei despite barriers that should confine them. It allows certain electronic devices to work. It makes possible the scanning tunneling microscope, an instrument so sensitive it can map individual atoms on surfaces. And, most profoundly for our daily existence, it plays a role in the nuclear fusion reactions inside stars. The The morning sunlight that slips through your curtains is connected to particles doing what classical physics alone would not let them do. That is quite a journey for something that began as a faint tale of probability. It is worth pausing on that feeling, not in a grand dramatic way, but in the practical sense of letting the idea become less foreign. A particle does not tunnel because the universe is careless. It tunnels because the particle is described by a wave, and waves do not always end abruptly at barriers. The wave fades through the barrier. Sometimes enough remains on the far side. Detection there is unlikely, but possible. With enough particles and enough attempts, possible becomes observable. Observable becomes useful. Useful becomes technology, starlight, and the slow ticking of radioactive atoms. The impossible, then, was not truly impossible. It was impossible only within the wrong picture. If you imagine the particle as a marble, tunneling made no sense. If you imagine the barrier as an ordinary wall and the motion as a path through space like a tiny thrown stone, it seemed absurd. But once the particle becomes a quantum object, once its probability wave is allowed to spread and fade, the situation changes. We are no longer forcing a marble through a wall. We are asking whether a quantum possibility can survive across a barrier. Sometimes it can. That does not make tunneling feel completely normal. It probably should not feel completely normal. Some ideas deserve to remain a little strange, like dreams where your old school has become an airport, or the way one missing sock can cause a household mystery lasting several years. But tunneling can become understandable. It can sit in the mind as a real process, not fantasy. A small particle faces a barrier. Its wave enters and fades. A little reaches beyond. The particle may be found there. That is the core of it. And now that the process itself is in view, we can begin to follow it outward into the universe. Because tunneling is not just an answer to a clever question about whether particles can pass through walls. It is part of the reason stars are able to shine steadily for billions of years. In the deep interior of the sun, where matter is hot, dense and restless, particles are constantly rushing, colliding and repelling one another. Classical physics alone would make their task far harder. Quantum tunneling gives them another route, not a broad road, not an easy passage, but a narrow chance that becomes powerful because the sun contains so many particles trying again and again. The same little principle that lets an electron cross a barrier in a laboratory also helps explain the light that warms the earth, reaches your window, and gently marks the difference between night and morning. Deep inside the sun, far below the bright surface we see from Earth, matter is crowded into a place so hot and dense that ordinary imagination starts to run out of furniture. There are no solid rooms there, no gentle yellow flames licking around like a candle, no tidy furnace door with a handle and a warning label. The sun is not burning in the everyday sense, the way wood burns in a fireplace or toast burns when someone becomes overconfident with the settings. It is shining because atomic nuclei are being pressed, heated and transformed in its core. The sunlight that eventually slips through your curtains in the morning begins as something far smaller and stranger, in a restless ocean of particles where heat, pressure, gravity and quantum tunneling all take part in one of the most important processes in the universe. For a long time, the sun was a puzzle. People knew it gave light and warmth. Ancient cultures saw it as a god, a clock, a life-giver, a golden eye in the sky. Later scientists understood that it was a physical object, not a lantern hung above the world for our convenience, though one must admit it does provide excellent service. But explaining how it could shine for so long was not easy. If the sun were simply burning fuel like coal, it would not last nearly long enough. Geological evidence showed that Earth was very old, far older than a chemically burning sun could support. Something deeper had to be happening. The answer eventually came from nuclear physics. The sun shines because light atomic nuclei fuse together to make heavier ones, releasing energy in the process. But even this answer contains a hidden difficulty. The nuclei that need to fuse do not naturally want to touch. The main actors in the Sun are protons, the nuclei of hydrogen atoms. A proton carries positive electric charge. Another proton also carries positive electric charge, and like charges repel. This is one of the simplest rules in electricity. Push two positive charges together and they resist. They do not greet each other warmly. They do not say, "Splendid, let us combine and make sunlight." They push apart. So for two protons to fuse, they must get very close enough for the strong nuclear force to take over. That force is extremely powerful, but it works only at incredibly tiny distances. It is like a very strong friend with very short arms. If the protons get close enough, the strong force can bind them together. If they do not, electrical repulsion keeps them apart. Here is the problem. Even in the core of the Sun, where temperatures are immense by everyday standards, most protons do not have enough energy to overcome that electrical repulsion in the classical way. If you imagine them as tiny charged marbles racing toward one another, the picture would be discouraging. They would approach, feel the repulsion grow stronger, slow down, and turn away before they came close enough for fusion. It would be like trying to roll two balls uphill toward the top of a ridge between them, only to have them roll back again and again. Classical physics would allow fusion only for the rare protons with enough energy to climb over the barrier completely. There are some of those because the Sun is hot and the particles have a range of energies, but not nearly enough to explain the steady shining of the Sun as we observe it. This is where tunneling enters quietly, not as a dramatic miracle, but as a small quantum allowance that becomes enormous because the Sun is enormous. The barrier between two protons is not a brick wall. It is an energy barrier created by their electrical repulsion. Classically, if a proton does not have enough energy to get over that barrier, it cannot get close enough to fuse. Quantum mechanically, the proton is not merely a tiny bead with one sharply defined path. It is described by a probability wave. As the protons approach one another, their quantum states allow a small possibility that they will be found close enough together for the strong nuclear force to take over, even when classical motion alone would have turned them back. They tunnel through the barrier of repulsion. That sentence may sound as though the protons are performing some delicate trick, like slipping through a locked gate while the universe looks the other way. But it is better to keep the earlier picture in mind. The probability wave reaches into the region that classical physics would not allow. It fades through the barrier, becoming very small, but not always vanishing before the critical closeness is reached. If the wave extends far enough, there is a chance that the protons will appear close together. Then the strong nuclear force can act and fusion can begin. The protons did not smash through the electrical barrier by brute force. They did not need to have all the classical energy required to climb over it. Their quantum nature allowed a tiny chance of getting close enough anyway. Tiny is the right word. For any particular pair of protons in the Sun, fusion is not easy. The chance is very small. A single proton in the Sun may wait an extraordinarily long time before it finally takes part in a fusion reaction. This is a good thing. If fusion in the Sun were too easy, the Sun would burn through its fuel violently and quickly, which would be inconvenient for many reasons, including but not limited to plants, oceans, breakfast, and the entire history of life. The Sun shines steadily because fusion is difficult but not impossible. Quantum tunneling helps make it possible, while the low probability helps keep it slow. The result is not an explosion that ends at once, but a long, stable release of energy over billions of years. There is something wonderfully balanced about that. Gravity squeezes the Sun inward, trying to compress its core. Heat and radiation push outward, resisting the collapse. Fusion provides the energy that supports the Sun against its own weight. Tunneling helps fusion happen at the rate needed for this balance. If the electrical barrier were absolute, stars like the Sun would struggle to shine as they do. If the barrier were too easy to cross, stars might live fast and die young, like cosmic fireworks with no patience. Instead, the quantum rules allow just enough leaking through the barrier for stars to glow steadily across immense spans of time. The universe, at least in this respect, seems to have found a rather elegant compromise. The journey from tunnelling in the core to sunlight on your face is not direct or quick. A particle interaction in the core releases energy, but that energy does not immediately fly straight out into space as the sunlight you see. The interior of the sun is dense. Light and energy scatter again and again, absorbed and re-emitted, redirected countless times. A photon born in or near the core may take an astonishingly long time to work its way outward through the solar interior. It is less like an arrow flying from a bow, and more like someone trying to leave a crowded room while every person politely but firmly redirects them into another conversation. Eventually energy reaches the outer layers and escapes into space as sunlight. Then, after travelling across the space between the sun and Earth, it arrives here, where it may warm a leaf, brighten a window, power a solar panel, or land on your eyelids just as you were hoping for 5 more minutes of sleep. The deep origin of that light is nuclear fusion, and the quiet helper behind much of that fusion is tunnelling. In the sun, hydrogen nuclei gradually combine through a chain of reactions that ultimately produces helium. Along the way, energy is released. Some of it appears as light. Some appears in other particles. Some becomes the heat and radiation that keep the star shining. The details of the full chain are intricate, and we do not need to chase every particle through every step tonight like anxious hosts at a crowded dinner party. The essential point is that the first steps require protons to get close despite their electrical repulsion. Tunnelling makes those close encounters possible often enough for the sun to shine. This also changes the way we think about sunlight. It is easy to treat sunlight as simple because it's so familiar. Morning arrives, the sky brightens, the room changes shape in soft gold or pale grey, depending on the weather and the mood of the clouds. But every bit of sunlight carries a history. It is connected to gravity gathering matter into a star, to heat stirring particles in the core, to nuclear forces acting at distances so small they are beyond ordinary imagining, and to quantum tunnelling allowing particles to cross barriers that classical physics would make too strict. A sunbeam is not just light. It is a message from the quantum world, delivered at a very comfortable scale. Tunnelling in stars also reminds us that quantum mechanics is not only about laboratories. It is not confined to delicate equipment, polished metal chambers, cold atoms, or scientists in protective glasses saying things like "interesting" in a tone that means either triumph or disaster. Quantum mechanics is operating in the most enormous natural objects we see. The sun, which feels grand, blazing, and classical in the sky, depends on tiny quantum probabilities in its heart. The same theory that describes an electron crossing a thin barrier in a device also helps describe the processes that make stars shine. The microscopic and the cosmic are not separate kingdoms. They are woven together. The very large often depends on the very small. In a sense, stars are powered by patience. Their cores contain vast numbers of particles moving at high speeds. Most encounters between protons do not lead to fusion. The particles approach, repel, and separate. Again and again, the barrier wins. But the sun has an unimaginable number of protons and an unimaginable number of attempts. When chance is small but the number of trials is enormous, rare events become steady. It is like hearing rain on a roof. One drop is small, one drop makes almost no difference. But countless drops create a continuous sound, a soft rushing presence. Fusion in the sun is not caused by one dramatic tunnelling event. It is the accumulated effect of countless tiny chances playing out throughout the core. That is one of the most important lessons of probability in physics. A low probability does not mean no effect. It means the effect depends on scale, repetition, and conditions. In a single quiet atom, tunnelling may be an occasional escape. In a solid material, many electrons tunnelling can become an electrical current. In the sun, countless protons tunnelling through their mutual repulsion help sustain a star. The world we experience is often built from many small probabilities added together. until they become something smooth and reliable. The glow of the sun feels constant, not because each particle interaction is certain, but because the numbers involved are so enormous that the overall process becomes stable. There is a pleasing humility in this. The sun, that great dominant presence in our sky, depends on events that are individually uncertain. It is steady because of statistics. It is bright because of tiny possibilities. It warms the oceans and drives the weather and feeds the plants because, deep inside it, particles sometimes do what classical physics alone would not permit. It is not chaos. It is not luck in the casual sense. The probabilities are governed by the rules of quantum mechanics, but the fact remains that the sun is not a simple furnace. It is a quantum engine under gravitational pressure, and its fuel burns by a process that requires particles to approach through a barrier they usually cannot cross. This helps explain why stars have different lives. The conditions in a star's core matter greatly. Temperature, density, pressure, and composition all affect the rate at which nuclear reactions occur. In more massive stars, cores become hotter and denser, allowing different fusion processes to happen more rapidly. Such stars can shine more brightly, but often live much shorter lives. Smaller stars burn more slowly and can last far longer. Tunneling remains part of the story. Wherever charged nuclei must get close enough for nuclear reactions. The barrier created by electrical repulsion is a common obstacle in stellar physics. Quantum mechanics provides the narrow passage through it. It is important not to imagine tunneling as making fusion effortless. The protons still repel one another. The barrier still matters. The sun still needs immense heat and pressure. Without those conditions, the tunneling probability would be far too small for fusion to proceed at a meaningful rate. Quantum tunneling does not replace the need for a hot, dense core, it works with it. The heat gives particles motion. The pressure keeps them crowded. Gravity holds the whole star together. Tunneling supplies the extra quantum possibility that allows some encounters to succeed even when classical energy alone would not be enough. It is a partnership between cosmic scale force and microscopic uncertainty. This partnership is why we should be careful with simple phrases like particles go through walls. It is true in one sense, but the real situations are often richer. In the sun, the wall is not a wall of stone or metal. It is an invisible barrier of electrical repulsion between charged nuclei. The tunneling particle does not pass through matter like a ghost through a corridor. It passes through an energy barrier in the quantum description, and the result is not a parlor trick but a nuclear reaction. The phrase is simple, but the meaning behind it is subtle. That is often how physics works. A small sentence opens into a whole landscape. Imagine for a moment the core of the sun as a crowded ballroom, though a very hot one and not at all suitable for formal shoes. Protons rush around in every direction. They come near one another and immediately feel the push of their matching positive charges. Most of the time they veer away. The music continues. The crowd shifts. Then, occasionally, because quantum probability has left a tiny opening through the barrier, two protons get close enough for the strong nuclear force to change the dance. A reaction begins. Energy is released. Not much from one event by human standards, but multiplied across the vast core, the result is the power of a star. The ballroom image is imperfect, of course, and any real proton would object to the dress code, but it captures the rhythm. Many encounters, few successes, enormous consequence. The slow rate of proton fusion is also tied to the long lifetime of the sun. This is a comforting fact. The sun does not spend its fuel recklessly. It shines with remarkable steadiness because the first steps of its main fusion process are difficult. Tunneling makes them possible, but not too easy. The result is a star that can provide stable energy for billions of years, long enough for planets to cool, oceans to form, life to develop, forests to grow, and eventually for someone to lie awake at night listening to a calm explanation of quantum tunneling. That chain from proton barriers to sleepy curiosity is not the usual way textbooks describe stellar evolution, but it is part of the same story. The energy released in the sun eventually supports nearly all life on Earth. Plants capture sunlight through photosynthesis. Animals eat plants or other animals. Weather systems move because sunlight warms the planet unevenly. Winds blow, rain falls, rivers flow, seasons turn. Fossil fuels, too, are ancient sunlight stored in chemical form by organisms long gone. Even the food in your kitchen is, in a broad sense, arranged sunlight. And behind that sunlight are nuclear reactions made possible in part by tunnelling. This does not mean you need to thank quantum mechanics every time you make toast, though it would not be entirely inappropriate. It means the gentle weirdness of particles at small scales is deeply connected to ordinary life. There is a tendency to think of quantum mechanics as distant from human experience, because it is hard to see directly. But the sun is not distant in its effects. It sets our days, warms our skin, grows our food, shapes our climate, and gives the sky its changing moods. The quantum processes in its core are hidden, but their consequences are everywhere. You do not need to see a proton tunnel through an energy barrier to feel the warmth that depends on countless such chances. Nature often hides its mechanisms behind familiar experiences. We feel sunlight first. Only later do we learn about nuclei, forces, plasma, probability waves, and the small impossible becoming merely unlikely. And perhaps this is a good place to notice how tunnelling changes the tone of the universe. Without it, stars would not behave the same way. The cosmos might be darker, colder, or at least very different. Fusion reactions would face stricter barriers. The formation of elements inside stars would follow other paths or occur under different conditions. The history of galaxies, planets, and life would not be the one we know. A phenomenon that sounds at first like a strange little exception turns out to be woven into the architecture of existence. Particles crossing barriers are not a footnote. They are part of why there is light. So when someone asks how particles can go through walls, the sun gives one of the grandest answers. They do not do it like people walking through brick. They do it because they are quantum objects, described by probability waves that can extend into barriers. In the sun, those barriers are made by electrical repulsion, and tunnelling lets particles get close enough for nuclear fusion to occur. Most attempts fail. Some succeed. Enough succeed to keep the sun shining. The result is not merely a curious effect in a microscopic world, but the bright, steady presence that has watched over every ocean wave, every leaf, every desert stone, every rooftop, every sleeping city. That thought can make the morning feel a little different. The light that seems so simple has passed through layers of physics on its way to you. It began with gravity holding a star together. It came from a core where particles rushed through heat and pressure. It depended on nuclear forces and quantum chances. It wandered outward through the dense solar interior, escaped into space, crossed the distance to Earth, and finally arrived quietly through a window, perhaps landing on a wall, a blanket, a cup, or the back of a hand. And somewhere deep in that story, at the scale where nature is less marble and more mist, tunnelling helped the impossible become ordinary enough to light the world. From there, it is only a short step, at least in the story, from stars to instruments and machines. The same principle that helps protons overcome a barrier in the solar core can be used by scientists and engineers here on Earth. Not to build little suns in our pockets, thankfully, but to measure surfaces, control currents, and design devices that depend on electrons appearing where classical physics would not expect them. Once tunnelling is understood as a real and reliable feature of the quantum world, it stops being only a cosmic secret and becomes a tool, one delicate enough to feel the shape of atoms and important enough to sit quietly inside the technology around us. Once tunnelling has helped us understand how particles can cross barriers in the heart of the sun, it becomes tempting to leave it there, glowing quietly in the centre of stars where everything is already strange enough to feel at home. But quantum tunnelling is not only a feature of distant plasma and nuclear reactions. It is also part of the technology sitting much closer to us, inside laboratories, computers, phones, sensors, memory devices, and instruments so delicate they can feel the shape of matter atom by atom. The same little quantum trick that lets particles slip through barriers they could never climb over in the classical sense has become one of the most useful tools in modern physics and engineering. It is not just a curiosity, it is a working principle, quietly doing its job while the rest of us tap screens, store photos, read messages, and occasionally wonder why the printer has chosen this particular moment to develop a personality. To see why tunneling became useful, it helps to return to the electron. Electrons are light, mobile, and deeply involved in the behavior of materials. They carry electric charge. They move through metals. They sit in the structures of atoms. They help form chemical bonds. They make electronics possible. If protons in the sun show us tunneling as a way through nuclear barriers, electrons in technology show us tunneling as a way to control, measure, and sometimes worry about the movement of charge. In many devices, an electron faces a barrier that classical physics says it should not cross. Yet if that barrier is thin enough, the electron has a chance of appearing on the other side. Put many electrons in the same situation, and that chance can become an electric current. Not a current caused by electrons rolling over a hill, not a current caused by punching through an obstacle, but a tunneling current. That phrase, tunneling current, is one of those quiet pieces of language that hides something remarkable. A current is usually imagined as charge flowing through a wire, like water through a pipe, though even that familiar picture has its limits. In a tunneling current, the charge crosses a region that would normally block it. There may be an insulating gap, a thin barrier, or a boundary between materials. Classically, the electron should not pass through easily. Quantum mechanically, their probability waves extend through the barrier. If a small part of that wave reaches the far side, some electrons can be found there. When this happens again and again, what began as a probability becomes a measurable flow of charge. The impossible does not become easy, but it becomes useful. One of the most beautiful uses of tunneling is the scanning tunneling microscope. The name sounds rather technical, perhaps like something that lives in a basement laboratory and requires a clipboard to approach safely. But the idea at its heart is surprisingly elegant. A scanning tunneling microscope uses an extremely sharp metal tip brought very close to the surface of a material, not touching it in the ordinary sense, just hovering above it at an almost unimaginably small distance. The gap between the tip and the surface is so tiny that electrons can tunnel across it. If the tip is moved across the surface while the tunneling current is measured, the current changes depending on the distance and the electronic structure of the surface below. Because tunneling is incredibly sensitive to distance, even tiny rises and dips on the surface can be detected. The result is astonishing. Scientists can build images of surfaces at the scale of individual atoms. Not by shining ordinary light on them, because atoms are far too small for visible light to resolve in the normal way, but by using the tunneling of electrons as a kind of quantum touch. The instrument does not see atoms the way an eye sees pebbles on a beach. It feels their presence through changes in tunneling current. As the tip passes over an atom, the gap changes slightly, and the current responds. Move the tip point by point across the surface, and an atomic landscape emerges. Hills and valleys of probability become a map. This surface of matter, which to us feels smooth and solid, is revealed as a landscape of arranged atoms, orderly in some places, rough in others, as if the material has its own hidden countryside. There is something almost tender about that. A sharp tip hovering over a surface, close enough for electrons to tunnel, but not so close as to crash into it. A current so sensitive that the height of a single atom matters. A machine that turns quantum uncertainty into an image. It is like reading a page without touching the paper, using only the faint possibility that letters might whisper across the gap. Of course, the real instrument is not sentimental. It is precise, demanding, and often requires careful isolation from vibration, temperature changes, and all the small disturbances that laboratories spend much of their time fighting. But the principle remains wonderfully subtle. Tunneling lets us measure what would otherwise be inaccessible. The scanning tunneling microscope did more than produce images. It changed what scientists could do with surfaces. In some cases, it can even move individual atoms around. By carefully controlling the tip and the tunneling interactions, researchers have arranged atoms into patterns, written tiny structures, and explored the behavior of matter at scales, where chemistry, physics, and engineering begin to merge. This is not the kind of technology that turns up in the kitchen next to the toaster, which is probably for the best, but it has shaped nanoscience, surface physics, and materials research. It gave scientists a way to work with matter at the level where quantum behavior is not a background detail but the main event. Tunneling also appears in electronic components designed specifically to use it. One example is the tunnel diode. A normal diode is a device that allows current to flow more easily in one direction than the other, rather like a one-way door for charge, though not one you would want to try to walk through. A tunnel diode is made with materials arranged so that electrons can tunnel through a very thin barrier under certain conditions. This gives the device unusual behavior, including a region where increasing the voltage can actually reduce the current. That may sound like the device is being difficult, but this strange feature can be useful in high-speed circuits and oscillators. Once again, quantum behavior that seems odd at first becomes a practical tool when engineers learn how to control it. Another important tunneling device is found in certain kinds of flash memory, the technology that helps store data in phones, memory cards, solid-state drives, and many other devices. Flash memory stores information by trapping electric charge in tiny structures inside a transistor. To write or erase data, electrons must be moved into or out of a region where they can remain stored. In some designs, tunneling allows electrons to pass through a thin insulating layer that would normally block them. By applying the right electrical conditions, the device encourages electrons to tunnel through the barrier. Later, the presence or absence of that trapped charge changes how the transistor behaves, allowing the memory cell to represent stored information. That means some of the photos, notes, messages, and forgotten screenshots on a phone may owe their continued existence to controlled quantum tunneling. It is a strange thought, a memory of a holiday, a shopping list, a half-written reminder to buy batteries, all resting in some way on electrons crossing barriers in tiny devices. The technology feels ordinary because we use it casually. We tap, swipe, save, delete, and complain about storage space. But inside the device, at scales far below what we can see, engineers are using the rules of quantum mechanics to move charge with extraordinary precision. The everyday has a quantum basement. There is, however, another side to tunneling in the electronics. Sometimes it is not a helpful feature. Sometimes it is a problem. As microchips have become smaller and smaller, the barriers inside transistors have also become extremely thin. A transistor is often used like a switch, controlling whether current flows or does not flow. Ideally, when the switch is off, electrons stay where they should. But if the barriers become too thin, electrons may tunnel through even when they are not supposed to. This produces leakage current. Leakage wastes energy, generates heat, and makes it harder to keep devices working reliably. In the early days of electronics, many barriers were thick enough that tunneling could often be ignored. As technology shrank toward the scale of only a few atoms, tunneling stepped forward and said, "Remember me." This is one of the great challenges of modern chip design. Engineers want smaller devices because smaller transistors can switch faster, use less space, and allow more computing power in the same area. But as parts become smaller, quantum effects become harder to avoid. The classical idea of a switch, open or closed, begins to blur slightly. Electrons do not always wait politely for permission. If a barrier is thin enough, they may tunnel through. So the same phenomenon that gives us useful devices also sets limits on how small conventional electronics can become. Quantum tunneling is both a tool and a warning. It helps us build technology, and it reminds us that the microscopic world has its own rules. This does not mean miniaturization simply stops. Engineers are inventive, and the history of electronics is partly a history of people finding new ways around physical limits that once seemed final. Materials can be changed, device structures can be redesigned, insulating layers can be improved, new transistor architectures can reduce leakage and maintain control, but tunneling remains part of the conversation. It is one of the reasons designing modern chips is not merely a matter of making everything smaller with a very determined shrinking machine. At tiny scales, every layer, every interface, every barrier must be considered quantum mechanically. The wall is no longer just a wall. It is a barrier with a probability attached to it. Tunneling also plays a role in superconducting devices. Superconductors are materials that, under certain conditions, allow electrical current to flow without ordinary resistance. They already belong to a somewhat unusual corner of physics, where electrons pair up and behave collectively in ways that would make a classical wire raise an eyebrow, if wires had eyebrows. When two superconductors are separated by a very thin insulating barrier, pairs of electrons can tunnel through the barrier together. This effect is used in devices called Josephson junctions. These junctions are extremely sensitive and can be used to measure magnetic fields, create precise voltage standards, and build elements of certain quantum computing systems. The Josephson junction is another example of tunneling becoming a technology of control. A thin insulating layer separates two superconducting regions. Classically, an insulator should block charge. Quantum mechanically, the paired electrons can tunnel through. The result is a current that depends on the quantum relationship between the superconductors. That relationship can be controlled, measured, and used. In quantum computing, superconducting circuits based on Josephson junctions can behave like artificial atoms, with distinct quantum states that can be manipulated. These systems are delicate and demanding, the sort of thing that does not appreciate being jostled, warmed, or asked to operate near a cup of tea. But they show how tunneling has moved from an odd effect in theory to a foundation for some of the most advanced technologies being explored. Another technology connected to tunneling is the tunnel magnetoresistance effect, used in magnetic sensors and in some forms of data storage. In these devices, electrons tunnel through a thin insulating layer between magnetic materials. The ease with which they tunnel depends on the relative orientation of the magnetic layers. Change the magnetic arrangement, and the tunneling current changes. This can be used to read information stored magnetically. The idea is subtle, but the result is very practical. A quantum tunneling effect helps translate tiny magnetic states into electrical signals. Once again, the particle does not simply obey the classical command to stop at the barrier. Its wave nature allows a measurable connection across a thin divide. It's interesting how often tunneling appears at boundaries, between a tip and a surface, between two materials, across a thin insulator, out of a storage layer, through a barrier inside a device. Tunneling is a phenomenon of edges and separations, of places where classical physics says one region should be isolated from another. Quantum mechanics softens the edge, not by removing it, but by allowing a faint connection across it. That faint connection can become a signal, a current, a measurement, or a problem depending on how the device is designed. The wall remains, but it is no longer silent. This gives technology a rather poetic feeling, although we will not linger too poetically because the transistors may become self-conscious. Modern electronics depends on controlling flows of charge. Sometimes the goal is to let charge move. Sometimes the goal is to stop it. Sometimes the goal is to store it. Sometimes the goal is to measure tiny changes in it. Quantum tunneling gives engineers one more way to shape those possibilities. If the barrier is arranged carefully, tunneling can be encouraged. If tunneling is unwanted, the barrier must be designed to suppress it. Every useful device is in some sense a negotiation with nature. You cannot simply command electrons to behave. You build conditions under which their probabilities produce the result you need. That is why quantum mechanics is not just a set of strange ideas floating above practical life. It is embedded in design. Semiconductor physics, lasers, sensors, memory, imaging devices, and quantum technologies all depend on understanding how particles behave in materials. The comfortable surface of a smartphone hides layers of solid-state physics. The storage drive in a computer hides carefully engineered barriers. Scientific instruments hide tunneling gaps controlled with extraordinary precision. When we say technology has become small, we do not merely mean physically small. We mean it has entered the realm where quantum behavior cannot be ignored. And yet, from the outside, these devices feel simple. You press a button, a screen lights up, a file opens, a message travels. The quantum details remain invisible, which is probably kind. Most of us do not want to think about tunneling currents when setting an alarm or checking the weather. But the invisibility should not fool us. Inside the ordinary action is a stack of extraordinary processes. Electrons respond to fields. Barriers shape probabilities. Charges move, store, leak or tunnel. Materials guide the behavior of particles with structures far too small to see. The device works because engineers have learned to make the quantum world reliable enough to become mundane. There is something remarkable about turning quantum weirdness into routine function. The first time someone hears that particles can tunnel through barriers, it sounds like a crack in reality. Then, after enough understanding, that crack becomes a tool. Build the right barrier, place the right materials, apply the right conditions, measure the current, store the charge, read the surface, use the effect. This is one of the great patterns of science. What begins as a mystery becomes a principle. What becomes a principle becomes an instrument. What becomes an instrument becomes part of daily life. Eventually the miracle is so well engineered that it has a warranty, a charging cable, and a tendency to need software updates at inconvenient times. The scanning tunneling microscope gives perhaps the clearest image of this transformation. Without tunneling, the tiny gap between tip and surface would be empty in the classical sense. No contact, no current. But quantum mechanics allows electrons to cross. The current depends so strongly on distance that the instrument can detect changes smaller than the width of an atom. In a very real sense, tunneling lets scientists feel the surface of the quantum world. It turns the faintness of probability into the sharpness of an image. It is hard to think of a better example of strangeness becoming clarity. Microchips show the other side, where tunneling must be carefully managed. The smaller the devices become, the more the quantum nature of electrons matters. A barrier that looks solid in a diagram may be thin enough for electrons to leak across. Designers must account for this, not as an afterthought, but as a central part of the physics. The chip is not a tiny classical city with electrons driving obediently down little roads. It is a quantum landscape of materials, barriers, fields, and probabilities, engineered so that the overall behavior becomes dependable. That dependability is what lets computers run, memories store, and circuits switch billions of times, without anyone needing to whisper encouragement to the electrons. Perhaps the most useful way to hold all this is to see tunneling as a controlled crossing of the unlikely. In the sun, it helps particles get close enough to fuse. In microscopes, it lets electrons cross a tiny gap and reveal atomic surfaces. In memory devices, it helps move charge through thin barriers to store information. In superconducting circuits, it allows paired electrons to cross insulating layers in ways that support exquisite measurement and emerging quantum technologies. In microchips, it can become leakage that engineers must tame. The same basic phenomenon appears in different costumes, always involving a barrier, a probability wave, and the possibility of appearing where classical physics would have said no. This should make us a little more respectful toward the devices around us. They may look solid, simple, and obedient, but they are full of hidden negotiations with the quantum world. A phone on a bedside table is not merely a slab of glass and metal waiting to distract you from sleep. It is a layered arrangement of materials that depends on electrons behaving according to rules far stranger than anything visible on the screen. Somewhere inside, barriers only a few atoms thick help store charge or prevent it from moving. Somewhere in a laboratory, a tunneling microscope may be scanning a surface with a tip so fine and a gap so narrow that the idea of touch has become quantum. Somewhere in a research system cooled to extreme conditions, superconducting circuits use tunneling to create controllable quantum states. The world of technology is full of walls that are not quite walls, and this leads naturally toward another place where tunneling matters, not in a device carefully built by engineers, but inside the atom itself. In radioactive decay, a particle can be trapped within the nucleus by forces and barriers that should hold it there according to classical thinking. Yet, given time, it may escape. Not by breaking the nucleus open like a prisoner with a hammer, and not by climbing over the energy barrier with energy it does not have, but by tunneling through the barrier in the quantum sense. The same principle that lets electrons cross a tiny insulating layer can help particles leave the nuclear interior, turning a sealed microscopic prison into something with a quiet probability of escape. Inside the atom, there is a place so small and so densely packed that the word small begins to feel underqualified for the job. The atomic nucleus is not merely tiny in the everyday sense, like a speck of dust or a grain of flour drifting through a sunbeam. It is tiny in a way that sits far below sight, below microscopes of ordinary kinds, below even the comfortable imagination we use when we picture atoms as little solar systems in school diagrams. And yet, inside that almost unimaginably small region, forces act with tremendous intensity. Particles are held together, pushed apart, confined, rearranged, and sometimes, after waiting for no predictable length of time at all, allowed to escape. This escape is radioactive decay, and one of its most elegant explanations is quantum tunneling. To begin gently, let us picture a prison. Not a gloomy one with iron bars and a rattling cup, because nuclei do not really go in for interior design, but a kind of energy prison. A particle sits inside the nucleus, held there by the powerful forces that bind nuclear matter together. In some radioactive atoms, the nucleus is unstable. That does not mean it is wobbling around like a badly stacked pile of plates, though the image is not entirely unhelpful. It means that the arrangement of particles in the nucleus can change into a more stable arrangement, and in doing so, something may be emitted. A particle may leave. Energy may be released. The atom becomes a different atom, or a different form of the same element. The change is not a chemical change, like rusting or burning, or the regrettable transformation of toast into charcoal. It is nuclear change happening in the deep compact center of the atom. One of the clearest cases is alpha decay. In alpha decay, a cluster made of 2 protons and 2 neutrons escapes from the nucleus. This cluster is often called an alpha particle. It is a very stable little group, and inside certain heavy nuclei, it can be thought of as existing for a while as a possible cluster within the larger nuclear structure. But there is a problem. To leave the nucleus, it must get past a barrier. The strong nuclear force holds particles together when they are very close. The electric repulsion between positively charged particles also matters, especially once the alpha particle is outside the tight grip of the nuclear force. The result is a kind of barrier around the nucleus, not a wall of stone, not a shell like an eggshell, but an energy barrier that classical physics would treat as a serious obstacle. Classically, if the alpha particle does not have enough energy to climb over this barrier, it should remain trapped. It might move inside the nucleus. It might press against the boundary of its prison again and again. But if it lacks the needed energy, it cannot escape. That is exactly the same logic as the marble in the bowl or the ball rolling toward the hill. Not enough energy means no crossing. The classical story is firm, tidy, and wrong for this situation. Experiments show that alpha particles do escape from radioactive nuclei even when, by classical reasoning, they should not have enough energy to get out. The nucleus behaves as though the prison walls are not absolute. Something subtler is happening at the boundary. The key is that the alpha particle is not a tiny classical pebble trapped inside a tiny classical box. It is a quantum object, described by a probability wave. Inside the nucleus, that probability wave is mostly concentrated where the particle is likely to be found. At the barrier, the wave does not simply stop. It extends into the classically forbidden region, fading as it goes. If the barrier is not too wide for the conditions involved, a faint part of the wave reaches beyond it. Once the wave exists outside the barrier, there is a chance that the alpha particle will be found outside the nucleus. When that happens, the particle has escaped. It did not smash the barrier. It did not climb over it with energy it did not have. It tunneled. This idea was one of the early triumphs of quantum mechanics. Radioactive decay had been observed before tunneling was understood. Scientists knew that certain elements emitted radiation. They could measure the rate at which samples decayed. They could observe that some nuclei changed into others. But why a particle could escape from a nucleus despite an energy barrier was a puzzle. Quantum tunneling gave an answer that was not merely poetic or suggestive, but remarkably accurate. It connected the energy of the escaping particle with the likelihood of escape. It explained why some nuclei decay quickly, while others remain for long periods. It turned the nuclear prison from an impossible trap into a probabilistic one. That word probabilistic is important. Radioactive decay is not predictable in the way a clock is predictable. If you have one unstable atom, you cannot say exactly when it will decay. It may decay in the next moment. It may not decay for a very long time. There is no little timer inside the nucleus counting down with theatrical suspense. The atom does not know it has an appointment. Quantum mechanics gives a probability of decay over time, not a scheduled departure. This is one of the most peculiar things about radioactive atoms. Individually, they are unpredictable. Collectively, they are dependable. If you have a large sample containing many unstable atoms, the overall rate of decay follows a reliable pattern. You cannot predict the escape of one prisoner, but you can predict how many escapes will occur from the whole prison population, given enough atoms and enough time. This is where the idea of half-life comes in. A half-life is the time it takes for half of a sample of radioactive nuclei to decay on average. If you begin with a large number of unstable atoms, after one half-life about half will have decayed. After another half-life, about half of the remaining ones will have decayed, and so on. It is not because each atom has a little calendar. It is because each atom has the same probability of decaying in a given period, and large numbers turn probability into a smooth pattern. The individual moment remains uncertain. The group behavior becomes predictable. This is quantum randomness wearing a very orderly coat. There is a gentle analogy, though like all analogies it must be treated with care. Imagine a large crowd of people in a quiet room, each holding a coin. At random times, people flip their coins, and those who get a certain result leave the room. You might not know which individual person will leave next, but if the crowd is large and the rules are consistent, you can predict roughly how the room will empty over time. Radioactive decay is not coin flipping, and nuclei do not stand around waiting for a signal from a polite usher, but the distinction between individual unpredictability and group regularity is similar. Quantum mechanics does not promise certainty for each atom. It promises reliable probabilities for many. The tunneling explanation also helps us understand why small changes in the nuclear barrier can produce very large changes in decay rate. The probability wave fades as it passes through the barrier. If the barrier is slightly wider or more difficult to cross, the wave may fade much more before reaching the outside. The tunneling chance becomes far smaller. If the barrier is thinner, or the escaping particle has more suitable energy, the chance increases. This sensitivity means that different radioactive nuclei can have wildly different lifetimes. Some decay almost immediately. Others persist for thousands, millions, or billions of years. The difference can come from how hard it is for the particle probability wave to make it through the nuclear barrier. This may sound strange, but it is exactly the same kind of principle we saw in technology. In a scanning tunneling microscope, electrons tunnel across a tiny gap, and the current is extremely sensitive to distance. In a nucleus, the probability of alpha escape is extremely sensitive to the barrier. Thin enough, and the particle has a meaningful chance. Too thick, and the chance becomes tiny. The setting is different, the scale is different, the particles are different, but the core idea remains familiar. A probability wave meets a barrier. It fades through the forbidden region. If enough remains beyond the barrier, the particle may be found there. Of course, a nucleus is not literally a little cage. It is not made of bars. It is not a hard container with a door someone forgot to lock. The forces inside it are deeply quantum and more complex than any simple picture can capture. Protons and neutrons are themselves made of smaller particles bound by the strong interaction. The nucleus is a many-particle quantum system, not a bag of billiard balls. But the prison image helps because it captures the essential puzzle. Something is confined. Classical energy says it should stay confined. Quantum tunneling says there is a small chance of escape. And when escape happens, we observe radioactive decay. The word decay can sound negative, as though the atom is rotting away like fruit left too long in a bowl. But in physics, decay simply means transformation. An unstable nucleus changes into something more stable, often releasing particles or energy. This can happen in different ways. Alpha decay emits an alpha particle. Beta decay involves changes related to the weak nuclear interaction, where one kind of nuclear particle transforms into another and emits other particles. Gamma emission releases energy as high-energy light from a nucleus settling into a lower-energy state. Tunneling is especially central to alpha decay and some related processes where a particle escapes through a barrier. Not every kind of radioactivity is the same, and not every kind depends on tunneling in the same way. But tunneling gives one of the most vivid examples of how quantum mechanics explains nuclear escape. A Geiger counter gives this invisible world an audible presence. Bring it near a radioactive source and it may click. Each click corresponds to a detected particle or burst of radiation interacting with the instrument. The clicks can seem random, uneven, clustered in one moment and quiet in the next. That randomness reflects the individual nature of decay. One nucleus decays now, another does not. Then another does. There is no steady drummer inside each atom tapping out a schedule. Yet if you listen long enough, and if the sample is large enough, the average rate becomes meaningful. The clicks create a pattern, not in exact timing, but in statistics. It is the sound of quantum chance becoming audible. There is something rather humbling in that sound. Each click may come from a nucleus that existed for years, centuries, or far longer before changing in that instant. Nothing obvious happened to trigger it. It was not waiting for a push in the everyday sense. It simply had a probability of decaying, and at that moment the quantum event occurred. The alpha particle, where alpha decay is involved, was no longer trapped. Its probability wave had allowed escape. The nuclear prison had not failed mechanically. It had always been a quantum prison, and quantum prisons come with probability in the walls. This also explains why radioactive dating can work. Certain unstable atoms decay at known average rates. If a material contains those atoms, scientists can compare the amount of the original radioactive material with the amount of decay product and estimate how much time has passed. This is used in geology, archaeology, and planetary science, with different isotopes suited for different time ranges. The method does not require knowing when each individual atom decayed. It relies on the statistical reliability of huge numbers of atoms. Quantum unpredictability at the individual level becomes a clock at the collective level. A strange clock, perhaps, but one that has helped measure the age of rocks, fossils, and ancient events in Earth history. So the same quantum tunneling that makes individual decay unpredictable also contributes to the reliability of natural clocks. That might seem contradictory at first, but it is not. Randomness and order are not always enemies. When randomness follows stable probabilities, large numbers can reveal smooth behaviour. It is like the patter of rain on a roof. You cannot predict exactly where the next raindrop will land, but you can measure the rainfall. You cannot predict which nucleus will decay next, but you can measure the half-life of a sample. The individual event is misty. The overall pattern is solid enough to build science on. Radioactive decay also reminds us that tunnelling is not always a gentle thing in its consequences. The process itself may be quiet, but the particles and radiation emitted can be energetic. Radiation can ionize atoms, damage biological tissue, fog photographic plates or trigger detectors. It can be dangerous in high doses, useful in controlled settings, and naturally present in small amounts in the environment around us. Some smoke detectors have used tiny radioactive sources to detect smoke. Medicine uses radioactive materials in imaging and treatment. Power plants use nuclear reactions to generate heat. The physics is neither good nor bad on its own. It is a feature of nature. What matters is how it is understood, measured, shielded, and used. There is a tendency to hear the word radioactive and imagine danger immediately, perhaps glowing green goo, mysterious barrels, or a laboratory with warning signs and someone backing away slowly. Real radioactivity is more varied and less theatrical. Many materials are naturally radioactive. The ground beneath us contains trace amounts of radioactive elements. Cosmic rays produce radioactive atoms in the atmosphere. Bananas even contain a naturally occurring radioactive isotope of potassium, though one should not regard fruit salad as a major radiological incident. The important point is quantity, type, exposure, and control. Physics helps us understand the processes clearly, without panic and without carelessness. At the nuclear level, tunnelling is a kind of escape route written into probability. An alpha particle may exist within a heavy nucleus, confined by the nuclear potential and blocked by a barrier. Classical thinking says it cannot leave unless it has enough energy to overcome that barrier. Quantum mechanics says its probability wave extends beyond the barrier, faintly but significantly enough in some nuclei. Once detected outside, it is no longer bound, it rushes away, carrying energy. The original nucleus is transformed. A new element may result. A tiny event has changed the identity of an atom. This transformation is one of the ways the universe rearranges matter over time. Radioactive decay changes elements. It heats planetary interiors. In Earth, the decay of radioactive elements contributes to internal heat, helping drive geological activity over long spans. That heat plays a role in mantle motion, volcanism, and the long restless life of the planet beneath its crust. So tunnelling, through radioactive decay, is connected not only to particles leaving nuclei, but to the warmth inside worlds. The ground under your feet, which seems so steady and classical, is part of a planet whose internal heat is partly sustained by nuclear transformations. Once again, the quantum world reaches upward into the familiar one. It is remarkable how often this happens. We begin with a tiny effect, almost hidden inside mathematics. Then we find it in stars, electronics, instruments, and atoms. Radioactive decay adds another layer. Tunnelling is not merely particles crossing barriers in controlled devices or protons helping the sun shine. It is also unstable nuclei quietly changing their identities, one unpredictable event at a time, while large collections keep time with statistical precision. The microscopic escape becomes a macroscopic fact. It becomes heat, dating methods, radiation detection, medical tools, and a deeper understanding of matter. The nuclear prison image then is useful but incomplete in a comforting way. A real prison has walls that either hold or fail. A nuclear barrier has probability. A real prisoner must find a door, break a lock, or dig a tunnel. An alpha particle does not do any of those things. Its quantum state extends beyond the barrier, and if nature gives the outcome on the far side, escape has occurred. This is not a story of effort. It is a story of possibility. The particle does not get tired. It does not plan. It does not become impatient after several million years and decide that today is the day. It simply exists in a quantum state with a certain chance of decay, and when that chance becomes an event, the nucleus changes. This can be both unsettling and beautiful. Unsettling because it removes the neat cause and schedule we often expect. Beautiful because it shows how order can arise from probability. A radioactive atom is not a broken clock. It is a quantum system following rules that do not resemble the ticking gears of ordinary machines. Its uncertainty is not ignorance in the everyday sense. It is part of how nature behaves. And yet, from this uncertainty, scientists can build precise models, date ancient stones, design detectors, and understand nuclear energy. The fog of possibility becomes a tool for knowledge. If we return to the question that started this journey, how can particles go through walls? Radioactive decay gives one of the clearest answers. The wall may be an energy barrier around a nucleus. The particle may be an alpha particle confined inside. Classical physics says it lacks the energy to escape. Quantum mechanics says its probability wave can extend through the barrier. Most of the time, the particle remains trapped. Sometimes the wave reaches beyond the barrier with enough chance for the particle to be found outside. When that happens, the nucleus decays. The wall was real. The escape was real. The path was not classical. And now the strange picture is becoming fuller. In the ordinary world, walls stop us. In the quantum world, barriers reshape probabilities. In the sun, tunneling helps particles fuse. In technology, tunneling helps measure atoms, store charge, and sometimes complicate the design of tiny devices. In radioactive decay, tunneling lets particles escape from the deep interior of nuclei, changing atoms and leaving traces we can detect. Again and again, the same quiet principle appears. A barrier says no in the classical language. A probability wave answers, not often but sometimes. And from that sometimes, the universe builds light, technology, radiation, and the long, slow transformations of matter. The next step is not to add another example, but to gather the thread gently and look back at what this tells us about reality itself. Because tunneling is more than a peculiar trick of particles. It is a reminder that the world beneath the surface is not made from the same kinds of certainties our senses present to us. Walls are still walls in daily life. Doors still matter. Hills still require climbing. But at the smallest scales, nature keeps a softer account of possibility, and the solid no of a barrier can become a faint but genuine maybe. After all this wandering through barriers, particles, stars, instruments and nuclei, we arrive back in the room where we began, with walls still standing quietly around us, and the ordinary world behaving, thankfully, in its ordinary way. The door is still a door. The floor remains beneath you. The cup on the table is not likely to tunnel into the next room in search of better company. Your blanket, your pillow, your window, your chair, all of them continue to respect the familiar rules of daily life, and that is a good thing. A universe where furniture regularly passed through walls would be exciting for about 3 seconds and then deeply inconvenient, especially for anyone living above a bakery. But underneath that dependable surface, in the places too small for eyes and too delicate for common sense, nature has been doing something far stranger all along. Quantum tunneling is not a break in reality. It is not a secret cheat code or a tiny act of disobedience. It is simply what can happen when particles are not treated as little marbles with definite paths, but as quantum objects described by probability waves. A barrier does not always mean an absolute stop. Sometimes it means the probability fades. Sometimes it fades so quickly that nothing useful remains. But sometimes, if the barrier is thin enough, if the particle is small enough, if the conditions are right, a little possibility reaches the other side, and where possibility reaches, a particle may be found. That is the quiet mystery of passing through. We began with the classical world, the sensible one, the one where a ball without enough energy cannot roll over a hill, and a person without a key cannot pass through a locked door without creating paperwork. In that world, barriers are firm. They divide here from there. They tell objects where they may and may not go. Classical physics describes that world with great success. It explains motion, force, energy, and the reassuring stubbornness of walls. It is the physics of bridges and bicycles, of falling apples and swinging pendulums, of mugs that fall when knocked and do not reconsider halfway down. For most of life, classical physics is more than enough. It gets us through the day with chairs that hold us, roads that carry us, and staircases that do not suddenly become philosophical. Then we looked more closely at the particle itself, and the tidy picture began to soften. A quantum particle is not just a small version of a familiar object. An electron is not a tiny bead with a hidden root. A proton is not a miniature billiard ball with a very small destination in mind. These particles are described by quantum states, by probability waves that spread out and tell us where they may be found. When measured, the particle appears in one place. Before measurement, the best description is not a definite little path, but a pattern of possibilities. This is the point where ordinary language starts to creak slightly, like an old floorboard under a careful footstep. We say wave, but it is not a water wave. We say particle, but it is not a marble. We say probability, but it is not merely ignorance. Quantum mechanics asks us to use familiar words in unfamiliar ways. The probability wave became the key. It can spread, it can fade, it can enter regions where classical physics says the particle should not be able to go. At a barrier, it does not always stop sharply. Part of the wave may be reflected, and part may extend into the forbidden region. Inside that barrier, the wave usually weakens quickly. But if a faint trace reaches the far side, then there is a chance of detecting the particle there. That is not the particle burrowing like a mole. It is not a marble smashing through concrete. It is not a ghost floating through plaster with poor manners. It is a quantum possibility surviving across a barrier. Small, subtle, and very real. This is why tunneling sounds impossible only when we hold on to the wrong picture. If we imagine an electron as a little pellet trying to punch through a wall, then tunneling feels absurd. But if we remember that the electron is described by a probability wave, then the question changes. We stop asking how a marble crossed an uncrossable wall, and we begin asking how much of a quantum wave remains beyond a barrier. That is a different question, and it has a different kind of answer. Most of the time the barrier wins. Sometimes the wave reaches through. The impossible becomes not guaranteed, not easy, not every day, but merely unlikely. And in a universe full of countless particles making countless attempts, unlikely can become important. The sun showed us how important. Deep in its core, protons rush through heat and pressure, pushed together by gravity and yet held apart by their matching positive charges. They repel one another. Classical physics alone would make many of their close encounters fail. They would approach, slow, and turn away before getting close enough for the strong nuclear force to bind them. But quantum tunneling gives a small chance that they will get close enough anyway. Not often for any single pair, but often enough across the vast crowd of particles in the solar core. That small chance helps fusion proceed steadily. Fusion releases energy. Energy works its way outward. Light escapes into space. After crossing the distance to Earth, it warms the ground, feeds plants, stirs weather, brightens windows, and occasionally wakes someone who was hoping the curtains would do a better job. So the light of the sun is connected to tunneling. That is a remarkable thing to hold in the mind. A process that sounds at first like a strange technical detail helps explain why stars shine. It helps explain why Earth is warm enough for oceans, forests, weather, and life. It helps explain why mornings arrive with more than darkness. The sun is not simply a ball of fire in the ordinary sense. It is a gravitationally held nuclear furnace, and deep inside it, particles rely on quantum chances to cross barriers that classical physics would make too strict. The warmth on your skin carries the history of those tiny crossings. The sky outside, whether bright with day or dark with night, belongs to a universe where probability can make stars possible. Then we came closer to home, into technology. Tunneling is not only a stellar secret, it is also a tool. In the scanning tunneling microscope, electrons tunnel across an incredibly tiny gap between a sharp tip and a surface. The tunneling current changes with distance so sensitively that scientists can map surfaces atom by atom. Matter, which feels smooth beneath our fingers, becomes a landscape of tiny rises, patterns, and structures. The microscope does not see atoms in the usual way. It feels them through tunneling. It turns the faint chance of electrons crossing a gap into a detailed image. There is something wonderfully practical about that. Quantum strangeness becomes a measuring instrument. In microchips and memory devices, tunneling appears again. Sometimes engineers use it deliberately, moving charge through thin barriers to store information or make special devices work. Sometimes they fight against it, because as components become smaller, electrons can leak through barriers that are supposed to stop them. A transistor that should be off may let a little current pass. A barrier that once seemed thick enough may become, at the quantum scale, negotiable. This is one of the reasons modern technology is not simply classical machinery made very small. At tiny scales, design becomes a conversation with quantum mechanics. The engineers do not command electrons like soldiers on parade. They build landscapes of materials, fields, and barriers where electron probabilities produce useful behavior. The result is the ordinary miracle of devices that work so reliably we mostly notice them only when they stop. Radioactive decay gave us another view of tunneling, this time inside the nucleus. In alpha decay, a particle cluster can be trapped inside a heavy nucleus by an energy barrier. Classically, if it lacks the energy to climb out, it should stay trapped. But the particle is quantum. Its probability wave can extend through the barrier. Most of the time, the particle remains inside. Sometimes it is found outside. The nucleus decays. A particle escapes from what looked like a nuclear prison. This escape is not scheduled in the ordinary sense. One atom may decay now, another much later, and no one can predict the exact moment for a single nucleus. Yet large collections follow reliable patterns. Half-lives can be measured, ages of rocks can be estimated, detectors can count radiation. Again, individual uncertainty becomes collective order. That may be one of the deepest lessons of tunneling. Nature can be uncertain without being careless. Quantum events may not give us the exact individual story we expect, but they give us reliable patterns. A single atom may decay unpredictably, but a sample of many atoms can become a clock. A single electron may or may not tunnel, but many electrons can form a measurable current. A single proton in the sun may wait an astonishingly long time to fuse, but the sun as a whole shines steadily. The quantum world does not replace order with chaos. It replaces one kind of order with another, one based not on definite paths and rigid certainties, but on probabilities so consistent that the universe can build stars, matter, and technology from them. And here we are, listening from the large world, the classical world, the world where walls still matter. That contrast is worth keeping. Quantum tunneling does not mean anything can pass through anything in daily life. You cannot walk through a wall by believing more deeply in probability. A tennis ball will not tunnel through a fence during a garden match, though it may vanish into a hedge in ways that feel almost supernatural. The effect is real for tiny particles under the right conditions, but for large objects made of enormous numbers of particles, coordinated tunneling through ordinary barriers is so fantastically unlikely that it has no practical meaning. The door remains the recommended method. This is not disappointing. It is what allows the world to be livable. We need the quantum rules underneath, but we also need the classical steadiness that emerges from them. We need electrons to behave quantum mechanically, so atoms can exist, chemistry can happen, stars can shine, and electronics can work. We also need walls to hold up roofs, cups to hold tea, and beds to remain in the room where we left them. Reality gives us both. At the smallest scales, it is soft with possibility. At our scale, it becomes firm enough to trust. The strange and the ordinary are not enemies, they are layers of the same world. Quantum tunneling also gives us a useful kind of humility. It reminds us that common sense is not the final judge of nature. Common sense is a fine tool for daily life. It knows about doors, tables, traffic, weather, and the importance of not touching a hot pan. But it was not built to understand particles smaller than atoms or barriers made of energy. When we enter that realm, we need experiments, careful reasoning, and sometimes a willingness to let go of pictures that feel obvious. The universe is under no obligation to behave like objects in a living room, and yet, with patience, even its strangest behavior can become understandable. There is comfort in that, not because tunneling is easy to picture, but because it shows that mystery is not the same as confusion. At first, a particle going through a barrier sounds like nonsense. Then we learn about the classical view of barriers. We learn that quantum particles are not marbles. We learn about probability waves. We learn that barriers can suppress possibility without always eliminating it. We see the same principle in the sun, in microscopes, in microchips, and in radioactive decay. Slowly, the mystery changes shape. It remains strange, but it becomes a known strangeness, a piece of the universe we can speak about without pretending it is ordinary. And perhaps that is one of the pleasures of science for sleep. We do not have to conquer the subject. We do not have to force every idea into perfect clarity before resting. Sometimes it's enough to let the mind drift through the structure of the explanation, collecting what it can: walls, waves, barriers, stars, electrons, nuclei. A little probability fading through a region where a marble would never go. The ideas may settle at their own pace, like dust in a quiet room or steam disappearing from a cup. You do not need to hold all of quantum mechanics in your head tonight. Even physicists do not hold it all at once. They return to it, test it, question it, use it, and still find it strange. So if your eyes are growing heavier now, that is perfectly allowed. The particles will continue tunneling without supervision. The sun will continue its nuclear work. Electrons will continue crossing tiny barriers in devices and instruments. Some unstable nuclei will decay at unpredictable moments, while large samples keep their statistical rhythm. The quantum world is not waiting for us to understand it before carrying on. It has been carrying on all along, beneath every wall, inside every atom, behind every beam of light. Before we finish, let me ask you again, gently. Where are you listening from tonight? What kind of wall is nearest to you now? Is it a bedroom wall, a window, a door, a ceiling above you, or perhaps the soft boundary between wakefulness and sleep? After all this talk of particles passing through barriers, maybe the most familiar barrier is the one we meet every night, the gradual crossing from the busy world of thought into the quieter country of rest. Thankfully, that crossing does not require tunneling through plaster or overcoming an energy barrier between protons. It only asks that the body relax, the breath slow, and the mind stop pushing quite so hard against the walls of the day. If this little journey has brought you some calm, or given your thoughts something gentle and curious to follow, I would be ever so grateful if you liked the video and subscribed. It helps this quiet corner of physics reach others who may want a peaceful way to learn, unwind, and drift closer to sleep. And if you know someone who enjoys strange science told softly, perhaps share it with them. Quantum tunneling may be subtle, but good company should not have to tunnel through an algorithm entirely on its own. So, sleep well, fellow traveller, wherever you are and whatever time it is in your small corner of the world. The walls around you are still solid. The night is still holding its shape. But deep beneath the surface of things, particles are spreading into possibility. Barriers are being tested by faint waves, and the universe is quietly reminding us that even the firmest no may, at the smallest scales, contain a very tiny maybe.